Okay, so anyway, we will complete if we have pending items. I will complete in the next lecture. Okay, so what let me start with a reminder of what we are trying to do here. Unfortunately, now the thing is that okay, this seems to share also this part in which I'm writing. Yeah. Okay. Yeah, unfortunately, it shares also the part on which I'm writing. So anyway, so this is the setting, what we set ourselves to do. We want to solve the ridge regression with a design matrix, or we want to use ridge regression with a design matrix that is this capital Phi and has potentially independent rows, and each row is obtained by mapping a d-dimensional vector through a featurization map into a p-dimensional vector. In the case, I remind you, in the case of two-layer neural network, p was equal to the number of neurons times the input dimension plus 1. Okay, and it had a special structure. And of course, ridge regression has an explicit solution, and okay, let me use this explicit solution for the sake of argument here. This can be written in two equivalent form. One is phi transpose phi times phi transpose y, and the other is phi transpose lambda in plus phi transpose y. Okay, and the second one is what will be useful for this lecture, and this identity is basically what the kernel tricks reduce to in the case of ridge regression. So what matters is, of course, is not the vector of coefficients b hat, but the model, and the model that we learn from this is let me call it f hat lambda of x, that is b hat lambda times phi of x. Okay, and
sorry, are you missing an inverse somewhere?
Oh yeah, I'm missing two inverses. Thank you. Okay, thank you. And so, of course, once you write out things, this is as the form f lambda of x is phi of x times times whatever you have here, right? So it's phi transpose, or let me write it even more clearly. Phi of x, this is a p-dimensional vector transpose, and then phi transpose, and then lambda I n plus phi transpose minus 1 times y. Now, what is interesting about this way of writing thing is that this depends on this featurization maps only through the kernel matrix. So we define the kernel to be, okay, kx1, x2 for a generic featurization map. This is phi x1 times phi x2 scalar product. And okay, I can introduce a kernel matrix K, that is matrix that is obtained evaluating the kernel at the data points. Okay, this is of course an n by n matrix. And in terms of this, the featurization map, the model looks like, it depends only on phi transpose. I mean, so we look like kx dot, let me write it and then explain you the notation that I'm using here, lambda in plus k inverse, and then y. And here the notation is that kx dot is just a vector whose entries are kx x1 blah 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 kx xn. Okay, if you want transpose This is, of course, an n-dimensional vector. Okay, so in our case, of course, if you look back to what we have to apply these things in our case. Okay, perhaps I'll go to the next page. These two, the featurization map is formed of two components. One is the random feature featurization map. So this is 1 over square root of n times sigma w1x blah 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 sigma w capital Nx transpose, and the other is what I call the NT featurization map, that is 1 over square root of nd times sigma w1 times x transpose blah 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 sigma wn transpose or wn times x transpose, and this is of length n times d, and this is of length n. Okay, so each of these gives rise to a corresponding kernel that is okay. I'll call them the kernel with n neuron RF x1 x2 is equal to 1 over n. So this is the scalar product of RF with itself, with the phi RF with itself. So this gives rise to sigma, wi times x1 times sigma wi times x2, and there is corresponding NT kernel that is 1 over n d, and then there is x1 x2, because when you take the scalar product you get this factor, and then sum over I. Mistake, this should be sigma prime. And then there is sum I1 to n sigma prime of wi x1 sigma prime of wi x2. Okay, so in this case, since you have capital N neurons, it's kind of these two kernels have this very nice structure in which they are sum of average of capital N terms, and on top of that, we know that wi are the weights at initialization. For different neuron, and the standard initialization is to take them IID, so independent in particular, with some common distribution, PW. Okay, on this is a distribution on RD. Okay, and of course the two examples that we have in mind is normal 0 ID over D, or uniform on the unit sphere. That for large D is nearly the same. So it's reasonable to think that by the law of large numbers, let me first, by the law of large number, this converges to some limit, and NT and converges to some limit as n goes to infinity, as the width of the network goes to infinity. Okay, and so why I'm saying is reasonable to think that well, it's obvious that this happens under some basic condition on sigma and on the distribution of W for any fixed x W1 and W2. So let me write what are these limits object KRF of x1, x2 is just the expectation with respect to W of sigma W x1, sigma W x2, and K and T x1, x2 is the expectation with respect to W. Okay, there is a factor in front, x1, x2 over D, and then the expectation with respect to W of sigma prime W1, W x1, sigma prime W x2. Okay, so a comment, I said that it's reasonable to assume that you have this convergence. In fact, if you are only interested in a weak form of convergence, that is pointwise convergence, that is you fix x1, x2, and you ask, do they, do Kn converges to K as n to infinity? This is obvious, it's just the law of large numbers. But of course, this is not sufficient to say much about the risk. Okay? The fact that at a given x1, x2, you have this convergence, this doesn't imply necessarily what you want. But okay, well, one thing that I'll mention and will be part of the content of the next lecture is that instead, this convergence happens in a stronger sense, and in particular, it implies convergence of the risk. So for the moment, we'll kind of postpone the question of clarifying what this convergence means in a quantitative way, and just pretend that we took n to infinity and then look at these two limiting kernels. Now, what is one important property of this kernel is that under these distributions, these are rotational invariant. That is, if I rotate both x1 and x2, the value of the kernel doesn't matter, doesn't change. So K of rotation of x1, rotation of x2 is equal to K of x1 and x2. Okay, so for simplicity, let's consider the case in which we fix the norm of the feature vectors, and to make sense, it has to be of order square root of D. So let's say that is equal exactly to square root of D. That doesn't really matter because it's just a rescaling in the activation function. And what this implies is that KRF of x1, x2 will become, just by rotation invariant, it can only be a function that I call HRF of x1, x2 of the scalar product, because the only invariant is the scalar product. And let me rescale the scalar product by D. And K and T is the same. Okay, so both of these must necessarily have the same structure. Okay, there is a question, I think, by Karthik.
Now in purpose, I figured it out.
Okay. Okay, so just one word about this normalization by the factor D here. Why this factor? I brought this factor D. In principle, of course, first of all, you can write more explicitly this function lowercase h, but of course, this in principle might depend on D. But I claim that the dependence on D of these two kernels it's very mild. In particular, if W is Gaussian, you can check that this is independent of D, H, RF, and H and T are independent of D. And you can write them, fairly explicitly as a one-dimensional integral, essentially, and or a two-dimensional integral. In general, for the other initialization that we have in mind, they are nearly independent, namely, this converge to a limit that is the same as the Gaussian case as D goes to infinity. Okay, so this means that basically these two functions, lowercase h, we can basically think of them as independent of the dimension. Okay, so now what we are interested in doing is understanding the risk of kernel ridge regression for rotational invariant kernel. Let me open a small parenthesis. If you consider a multi-layer fully connected network, okay, so F. So let's open a parenthesis and look for a moment at a more complicated model in which I have L layers. Okay, so these are my matrices, and then there is a sigma activation in between. Perhaps I should write this a bit more explicitly, but sigma times WL minus 1, and blah, 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 until W2 composed with sigma times W1, and here sigma are the activation function and W are the weights. Okay, you can, of course, the neural tangent theory, you can always define it and study it, and of course you end up with a kernel that is for the L layers thing is just defined in general as the gradient with respect to the parameters of fx theta 0, x1 theta 0. Now, if I take the W with a rotationally invariant distribution at initialization, so W, let's say L ij, for instance, IID, normal 0 tau square L. Okay, so all the weights in this network are Gaussian with the variance that depends on the layer level. Just by invariance of the Gaussian distribution, what you obtain is K and T must be rotationally invariant. So this is the finite width object, and if you look at this expectation over the initialization, this must be rotationally invariant. In particular, if xi are all normalized to have norm square root of D or whatever norm that you have, then K and T, x1, x2 will also be H and T. Let's say with L layers of x1, x2 over D. Okay, So all that I'm going to say actually applies to any rotational invariant kernel, and as a consequence applies to also the kernels that you obtain by 50 layers neural networks, as long as these are fully connected and they have this specific initialization.
Andrea, you don't need the later layer weights to be Gaussian, do you? Don't you just need the first layer to be Gaussian? Is that true? Am I missing something?
Good question. I think you're right. Unless I'm missing something, I think that you're right. So, yeah, I thought something similar, but
okay. Yeah, thanks.
Okay, somebody can sending a link on this specific question. Yeah, I'm not 100% sure, but yeah, and right now it seems that you're right. Anyway, I'm sure for multi-layers because we thought this through. Okay, now the things that I will say about the following setting. I'll assume the data to be also uniform on the sphere. And I'll take so this is a very specific distribution, but I'll take a kind of quite general model for the responses. That is, y are some function of the xi plus arbitrary noise. Let's say normal. I write normal, but this doesn't really matter in the proof. Independent. And okay, the only assumption that I make about the target function is that it is square integrable. It needs to be square integrable because we are looking at square laws, and if it is not square integrable, things are not well defined. And okay, one more assumption. So this is basically for simplifying my life, but it's not really important. This function h that captured the rotational invariant kernel is generic. So what do I mean by generic? In this case, I mean the following: take h, and okay, this is a function, reals to reals, of course. And you can write its decomposition in Hermite polynomials. Okay, these are Hermite polynomials. And what I'll assume is that all of these coefficients are different from 0. It's easy to check that they are all to be non-negative, but I'll assume that they are all non-zero. And bounded away from 0 if this thing depends on D. Now, in reality, for the statement, for obtaining the theorem that I'll give you, that I'll state, you don't need such a strong assumption, but even this is quite mild. If you take, for instance, you take ReLU and you shift it by a little bit, then you obtain it satisfies this assumption. ReLU by itself doesn't satisfy it, but because ReLU is symmetric, basically, is equal up to a linear function is equal to the absolute value, which is symmetric. So it's very degenerate. Okay, now, so what we want to understand is the generalization properties of kernel ridge regression with invariant kernels on this model. Right, so this is a theorem, and okay, so this is a theorem with Berus-Corbani Theodore Misha, who is TAing, Song Mei, and this was published in 2020, I think. And the theorem says the following. Assume that basically the sample size. Now we have two parameters, right? The input dimension and the sample size, and the assumption. And we looked at a regime in which these two are polynomially related, right? You can look at many different asymptotics. Here we look at the case in which both D and N are large, but they are not necessarily proportional, right? They are in general related as polynomials. And special things happen when the exponent of the polynomial is an integer. So basically what I'm assuming here is that the exponent of the polynomial is not an integer. Okay, so this is for some L a natural number and delta a positive number. Right? So what I'm ruling out by this assumption, and now I see that what I'm ruling out by this assumption is n equal d to the k for k, or proportional to d to the k for k an integer. So this is the real case that, and for simplicity of the proof, I give a little leeway. So then the risk looks very simple. I didn't say anything about the regularization for any lambda between 0 and lambda star. Lambda star is a positive constant. The risk of this kernel ridge regression with the regularization lambda and on the target function f star is equal to the projection of f star onto a polynomial. Okay, let me write it and then explain the notation here. Okay, so what is the notation here is if you have any function, this object is a projection the orthogonal projection of G onto polynomials of degree bigger than L. Okay, in other words, it's the projection orthogonal to polynomials of degree less or equal than L. Okay, you take the function G, or in this case, the function f star, and you subtract its projection onto polynomial degree less or equal than L. And this is what P bigger than L means, right? And the projection is, of course, so the projection is what is in L2 of the sphere with uniform measure. Okay, which is the distribution of X. And what is this norm? This norm is also the norm in the same space. So there is a second part of the theorem. So this is the parenthesis, second part of the theorem that says further no kernel method for every kernel. Let's write it. Okay, no kernel method can do better. within a product kernel. Does better. Okay. Okay, perhaps I should pause to ask if there is any question here.
Hi, just to clarify, for the polynomials in here, do you refer to just regular polynomials with degree L, or is it Hermite polynomials?
Regular polynomial, but it's the same. But these are polynomials in the dimension. Okay, so you take the polynomials in the dimension, and you can think of it also in terms of spherical harmonics, but it's the same. I mean, so you are projecting orthogonally to the first L, all the spherical harmonic up to spin L, as you say in physics. So Sam had a question.
Thanks. I might have missed it. Sorry. What is the phi here? I'm looking at the little o phi. Am I reading it wrong?
So okay, this is little o in probability.
Oh, okay.
Sorry. So what does it mean, little o in probability? Is something that goes to the left-hand side is a random quantity, right? Because it depends still on the sample points, on the noise realization and whatnot, right? So the left-hand side, I define the as risk only taking expectation with respect to the last noise, and small o in probability is something that goes to zero with high probability, let's say, or is smaller than any epsilon with high probability. Okay, so let me make a couple of comments.
Can I ask a quick question, Andrea?
Yeah, sure.
So just as a kind of interpretation, is it fair to say that this theorem kind of says that basically no kernel method can beat, the curse of dimensionality here, because you need n to be kind of polynomial in the dimension if you want to learn the, polynomials of the degree that you want, essentially. You have to have enough data points to actually determine them. And that, these kernels actually achieve that up to some constants.
Right. Now, exactly. So there is an element of curse of dimensionality here. At the same time, okay, so let's see. At the same time, so perhaps let me go by order. Okay, perhaps let me start with your remark. So let me remark one, perhaps. Let's say if n, or this is an example, is less than d to the 1.99, I can only learn linear functions, or the linear component. I mean, if I want the left-hand side, the right-hand side to go to zero, you need, in this case, to have the projection onto polynomials of degree bigger than 2 to be zero. Can only learn linear functions. If the function is nonlinear, you cannot learn it consistently. If it is truly nonlinear, in the sense of having a projection onto degree 2 or 3 or 4 polynomial bounded away from zero. Now, it must be said that parameter counting tells you that to learn any degree 2 polynomial, or all, let's say. Here I'm a bit informal, but so on one hand, you can say, okay, this is very bad because I need the d-square parameters. But if you want to learn all degree 2 polynomials, you need d-square parameters. the d-square samples. So on this, there is no way out, right? Any method just by information theoretic reason needs this square parameter. Well, what's bad here is that these kernel methods are bad for all F stars. For all, let's say for all S star. Namely, what this phenomenon describes is that up to d.199, you don't learn any degree 2 polynomial, and at d.201, you learn all of them, right? So it's not that very complicated degree 2 polynomials take more samples than simple degree 2 polynomials. In other words, if I think of the risk curve as a function of, let's say log n over log d, okay, so this is the exponent, then you can think that the risk curve goes like, for any given function as a staircase for a very large n and very large d, it will have a kind of staircase behavior where the steps of the staircase are at the integer. Okay, and the level of the staircase are, the projection of the function onto the first level is, and so on. This level is projection bigger than 2F star, etc. Okay, so this is the picture. Let me also point out briefly that one other way of stating the theorem is that really, if you look at f hat lambda, this is equal to projection of f star onto low degree polynomial plus an error delta, and the error delta is small. This is just an equivalent formulation of the theorem. Okay, so you really learned, what kernel ridge regression is doing is a projection. Okay, so one second last remark, perhaps, because, or second remark, I don't know, perhaps I'll do a third one. The second remark is that lambda equals 0 is optimal in these intermediate, in these regimes. Why it's optimal? Well, we read it out of the theorem because this achieves this result for any lambda between 0 and some lambda star. So as long as lambda is smaller than something, including 0, it works fine, and this it's better, as you see here. No kernel method can do better. In particular, ridge regression with a larger lambda doesn't do better. Lambda equals 0, what corresponds to interpolation. And perhaps one last remark about this result. This result excludes the case, as I said, when n is proportional to an exponent. Well, there was one case that was studied in more detail, and this is, okay, joint work with And there, what you see is that, okay, this, when you blow up, okay, what I traced before is this kind of staircase behavior. But if you blow up this, you see something, much more structure. You see that this is, for instance, for lambda equals 0, it has a divergence, the risk. So this, I'm always tracing the risk as a function of now n over d, perhaps. And okay, so now this is really, yeah, sorry, mistake. This is really as, this is for the random feature model. But okay, you can trace, what I meant to say is that in general, you can trace, in this regime, you can compute exactly the risk. And now, in this regime, it might be that lambda is not optimal, depend on the SNR. So if you look, if you blow up the curve where n is proportional to d, you can get, depending on the level of the SNR, that lambda equals 0 is perhaps suboptimal. And if you add n less than infinity, you can get a divergence at the interpolation threshold. But okay, here I was wrong. This is not really a function of n over d. So perhaps I'll erase this curve. Okay, so I want to say just that when you go to the proportional regime, you can compute the curve and precisely, and then you can get, depending on the SNR, that it's not necessarily true that interpolation is optimal. Okay, so as announced, I cannot stay, actually I must leave a couple of minutes earlier. So perhaps I'll ask you if there is any question.
I have a very brief question, Andrea.
Sure.
So suppose you start requiring the distribution of the x's to be a little bit more exotic than uniform on the sphere. Mm-hmm. Maybe it's like almost concentrated on like a lower dimensional submanifold or something of that form. How much of this can you push through? Things won't quite be rotationally invariant anymore, but there's still some kind of Weil laws. There's some kind of, there are estimates on the decay of the eigenvalues and all of this and on eigenfunctions.
Okay, that's a good question. So there is one case, there are a couple of things that we did. Okay, first of all, I should say, we wrote a long paper in which we give general conditions under which these kind of things can be computed in the same way. So there is a general theorem that you can use, and then you can plug in whatever distribution you want and get in this kind of staircase phenomenon. Now, coming to the idea of a low dimensional structure, there is one case that we studied. Okay, so one structure that you can imagine of imposing is a low dimensional thing, and of course the simplest idea would be that you have a low dimensional hyperplane. So perhaps your data points lie close to this. So you can imagine that perhaps the xi are like this. So it's a for instance, Gaussian distribution, but it has some eigenvalues that are large. The covariance has some eigenvalues that are large, perhaps a very few of them, and some that are small. And there is a subspace. Okay, so now this example, we studied it in detail. So we have a paper in which we studied this, and you get that basically the same picture goes through if you replace dimension with something that we call the effective dimension. And the effective dimension is something that interpolates between this D1 and D.
Right, okay, that makes sense.
And okay, let me mention another case that is interesting to study, and we studied to some extent, is if you take, instead of inner product kernel, you go to convolutional kernel. So for some special models of convolutional kernels, we could push this whole calculation through, and you get some measure of how the convolutional structure improves. I mean, what happens is you don't have this staircase at d to the L, basically, where L is the degree of the polynomial, but d to the L minus 1.
Okay, I see. Great. And this is all linked from your review article, I assume.
Yeah, it's linked, and you should be able to find.
Okay, great. Thanks very much for the lecture, Andrea.
Thanks to you guys, and sorry for rushing out. Bye.
Okay, everyone. Well, the next lecture is going to be at 12:30 Eastern, so in about 33 minutes. If you all have more questions for Andrea, you can either try to ask him during the final lecture, or you can go to the TA session, which is tomorrow afternoon, I believe. Let me double check. Yeah, that's right. So I think Theodore will have another TA session. Yeah, otherwise, see you all in about half an hour, hopefully. Yeah, we can see the screen. We were having some trouble earlier with that, but this seems to be working just fine. You want to try clicking just to make sure we can see the slides move?
Let me try this.
Yeah, that's perfect. Okay, excellent. Let's just give people another minute to arrive here, but seems to all be working fine. Hope you're doing well, Misha.
Yeah. How about you, Boris?
Yeah, doing fine. Doing fine. You know, lots of work, but also lots of time. So it all kind of works out fine. That's the best thing. There are 24 hours in a day. It's pretty good. You know?
You think sleep is overrated?
Well, no, I incorporate all of it. You know, you can get enough sleep, and then there's still lots of time in which you can do a lot of work if you have a lot of work to do. You know, like imagine if there were like 12 hours in a day. Now, of course, it's a silly thing to say, but still.
Fair enough.
Yeah. Okay, so maybe let's get started. Welcome back, everybody. I assume people will pile in the next 30 seconds or so, as they usually do. But okay, we're very happy to have Misha back for, I think this is lecture number 4. Is that right, Misha?
3, I think.
This is 3. Did I miscount? Yeah, you're totally right. This is
Yeah.
number 3. Okay, excellent.
Okay, thanks, Boris. So great to be back. Yeah, so the plan for today is to do the following. First, I'll start by summarizing some of the material or some of the ideas that we discussed before. And then sort of the main discussion today will center about what to do for parameterized model. And in particular, I'm planning to do a very quick overview of what kernel machines are, and linear regression is sort of very, very condensed summary of certain key things, which hopefully will bring the things together. So, okay, so let's start. First, as we have seen, so the key aspect of the theory crisis in machine learning has been the apparent lack of overfitting, which was sort of, it was an old observation in a sense, but it was kind of hammered down by the way that people use neural networks. And the specific theoretical question, and that this idea of this prism, is that instead of talking about overfitting in general, to think about why and when does interpolation generalize. And as we have seen so far, is that classical complexity-based analysis basically completely failed. There is no hope to explain the things from uniform laws of large numbers. Alternative methods, like one nearest neighbor classify simplicial interpolation and this weighted Nadari-Watson on nearest neighbor schemes, actually generalize probably and show some blessing of dimensionality, which is at least somewhat indicative of what's going on in deep learning. But as we have seen, these are quite different types of methods from what is used in machine learning currently, or at least what is sort of most commonly used. And finally, adversarial examples are a side effect of interpolating noisy data, so that fits quite nicely with this general scheme of general approach to understanding. So what are the key outstanding questions? And the first question is, well, it's probably the key question, is that what about parametric schemes, and in particular neural networks? And this is what we're going to talk about today. And second, which is a question whether interpolation is actually necessary or desirable. And I think the second question is kind of subtle, and it's clearly that exact interpolation is not necessary, but is it desirable? And you can argue both ways, and we'll discuss why it might be desirable, in particular with respect to optimization, but not this lecture. Next lecture on that. Okay, so now let's get to parametric families. And here we're going to start with a simple experiment, which you have seen some version of this in Adit's tutorial already, but let me repeat. So what you take a ReLU network, and what is a ReLU, right? ReLU of x is simply max of x and 0. And the network is particularly simple. You just have one hidden layer of size d, okay? So it's a function of the following form, is that sum alpha j ReLU bj of x plus cj, where bj of x and cj and alpha j are all real numbers. So it's a one-dimensional. X here is one-dimensional. And we're just going to consider random ReLU features, which mean that B, J, and C, J are chosen at random. Okay, it's not extremely important how exactly is the random. So these two are random and they're fixed, and we're only training alpha J. And once you think about it, you realize this becomes simply linear regression in this setting because, well, the nonlinearity is fixed. It's what's called a feature map. So we're just trading this by linear regression. So this is the setup, and we'll discuss related things to this more. But for now, I think we need to look at the experimental results to get some intuition about what's going on. And the experimental results are like this. So red points here, red dots, just data in one dimension, so it's just x and y, okay? And the task here is regression. And if you have 3 random ReLU features, so d equals 3, you get this curve, which you see on the left, which you kind of think is kind of a reasonable fit to the data. When you increase the number of random ReLU features to 30, which is more than the number of data points. The number of data points is 11 here, I think 11 or 12. So 30 is more, but it's not dramatically more. It's a little more than the number of data points. And you get this kind of very wiggly curve, which it's a kind of a bad fit to the data. But what is interesting is that when you increase the number of 3,000 ReLU, the number of ReLU features to 3,000, so way, way more than the number of data points, you get this beautiful smooth curve. So on the left, you can kind of think, well, if you have some parametric model, so this is, you can think of the parametric model, that's what it should do. This is some sort of classical overfitting. And this is the one on the right. It's kind of interesting because this is actually a fairly nice curve, and you can say this is a non-parametric. For those of you who are familiar with this type of models, it's a non-parametric fit. Actually, it's a kind of spline. Okay. So what is going on here? How do we explain these observations, and what is the meaning of these observations? And I think the easiest thing to think about here is that if you want a good fit to the data just very intuitively, small number of parameters is okay, and large number of parameters is also okay. But medium number of parameters is somehow not so good. And actually, just as an aside, I think in machine learning, I think a lot of developments in machine learning, effectively my own research, have really been shaped by the experimental results. In some sense, I'm viewing it more and more as physics, that we're observing certain phenomena, things like that. And then we're trying to build model and trying to understand where they apply and how they apply and how can we understand that theoretically. So I think looking at what happens and trying to explain it is really important, rather than going from a purely theoretical point of view, which is also sometimes useful. But in this case, theory can give you right ideas, but theory can also mislead you sometimes. And I see that Darshil raised hand, so please go ahead.
Hi, so this is probably sort of a premature question, but you said that the large parameter case is also okay, but it's not quite okay, right? Because if the data points you have were like sort of derived from a noisy line, then this fit is not exactly okay, because it's like very, very much different from a line. So
that is not completely clear, right? Because we discussed that sometimes so the question is, here it doesn't look very spiky, but imagine if it was very spiky, like what I had before in one of those pictures, and it would be okay even fitting this way. So it depends on the exact nature. This is a specific setup. And I agree with you that if the data were much more noisy than this, it would not look so much okay here. It would also. But if you somehow can force it to be more spiky than this, you would still be.
Okay. Thank you.
It's not spiky enough in some sense. This is too smooth. Okay, so now how do we explain this? And I think we have to go back to trying to talk a little bit about linear regression. And I'm just going to do a very brief review of linear regression and kernel machines and see what does even linear regression do. So hopefully, I mean, many of you probably already have these intuitions, but I think it is still helpful to go over it and think this through or see it one more time. So let me switch to, I'm going to switch to iPad. Easier. So linear regression first. What is linear regression? Linear regression is you have data xi, yi, right? I equals 1 to n. And you basically want to find w such that xi w equals yi. When I say equals, it may be approximately. Okay, for all. So find w. In statistics, this is often denoted as beta. In machine learning, more frequently as w. Okay, so if you think about what this means, this is simply solving an equation xw equals y, right? From a point of view of linear algebra, right? This is just solving xw equals y when x is your data matrix. Now, this is kind of interesting, just as a small aside. You know, when we take or when we teach linear algebra, we actually always talk about square matrices, right? Solving linear equations when the matrix is square, right? You have ax equals y, and then you solve it by inverting a. Almost never do we talk about matrices which are not square. But actually, if you think about it in real life, the matrices are rarely square, if ever. And so in some sense, this is a really fundamental question. How do you solve a linear equation when the number of variables is not equal to the number of equations? Rarely discussed. Okay, in any case, so how do we solve such a thing? So suppose now classical case, so classical, with d is smaller than, and I am assuming that xi is in RT, okay? Then d is smaller than n, so there are more data points in the equations. And then equation, the solution w, which makes this exact, doesn't exist. So the way we do it, of course, we do w star is equal to argmin over w sum xi w minus yi squared. We can put 1 over n here, and which is just simply argmin norm w. How does it work? X w minus y, when this is a vector of y, I should say, of yi squared, right? So this is just argmin of this. And this has a very natural geometric interpretation because, well, if you think about the vector xw, so think about the span of xw. So this is xw for all possible w's, right? That is a hyperplane in, so this is the hyperplane in what? In Rn, right? And you have y here, so the vector of y's. And now we're trying to find w, so we're trying to find a point on this plane which, you know, is closest to w, because that's the meaning of the norm. And this is nothing else but the orthogonal projection of y to the span of xw. So that's a geometric interpretation for the standard solution, which I'm sure we have all seen. Now, if you want to write this explicitly, you can write this as AW star is equal to x transpose x to the minus 1 x transpose y, right? This is the solution. So yeah, and this is known as the covariance matrix. Now, of course, this one is, you know, we understand quite well. The question is, what happens when d is bigger than n? So what about d bigger than n? And actually, if d is equal to n, you can just invert the matrix because, you know, assuming it's full rank, it will be invertible. So what happens when d is bigger than n? Here you have, so you can say w star is equal to argmin of xw minus y, right? The same way as before. And of course, very quickly, you realize that this is a set. Now, instead of just having one solution or no solutions, as when in d is smaller than n, you have infinitely many solutions. So you cannot say that you just choose any solution. And this actually goes back to this fundamental problem with interpolation and uniform bounds, because if you say uniform bounds, you somehow have to bound over any possible solutions, but there are infinitely many of them. This is a big problem. There are infinitely many solutions which fit the data exactly. So what does it mean? That means that we have to choose one of the solutions. So which solution do we choose? Choose a solution. And here it kind of reversed. So if you think about before, we had this xw, and we find the orthogonal projection, the point which is closest in xw to y. Now, we actually kind of invert this, and we look at the space of all possible solutions. And we choose w star here, and w star is argmin of norm of w star squared in the set of xw equals y. Okay, so in a sense, oh yeah, I saw there were some comments. Yeah, the g here is number of parameters, which is how do you think about it, right? It's the length of the vector w, which is the same dimension as x here. Okay, so w star is the smallest norm solution it's the smallest known solution within the set of all solutions, which is actually an affine hyperplane. So it turns out that there is also an explicit expression for this, the expression is the following: W star is equal to X transpose X transpose to the -1 Y. Okay. Now this is quite interesting because, well, this actually is known as the kernel matrix. And notice that the covariance matrix is D by D. The kernel matrix is N by N. I'm assuming here that the kernel matrix, of course, is invertible. But it doesn't have to be. And here we have this idea of the pseudo-inverse, which is actually the following. And let me write this identity to you first, and then I'll make some comments about the pseudo-inverse. So xt, xt to the -1 y. So what I would like to say is that this is equal to x xt x to the -1 xt, right? Y. And I don't really need y here. What I would like to write is something like this. Notice that there is a problem. Is that I want to say that this is true, but I cannot, except for the case when D is equal to N. Why? Because, well, the rank of this matrix is D, right? So this is rank at most D. The rank of this is N. So the ranks of those two sides don't match. So they cannot be both invertible at the same time. Right, because we know on one hand side X transpose X and XX transpose have, and I'm not saying this correctly, the ranks of those two matrices is the same. Sorry about this. So rank X transpose equals rank X transpose X. But the sizes don't match. So they cannot be invertible at the same time unless K is equal to N, D is equal to N. So that's so that identity cannot hold unless you have D equals N. So what you can do, however, you can fix it, and what you can do, you can put pseudo inverse instead of inverse, and then you put the plus here, and you have X transpose X plus X transpose. So instead of inverse, you take pseudo inverse. And the easiest way to think about pseudo inverse, what is pseudo inverse for, well, so pseudo inverse is actually defined for a matrix which doesn't have to be square, but it's easier to define it for a square matrix. So what you do, you take the inverse, and if you take the inverse of a matrix, right, your eigenvalues get inverted. So some eigenvalues will be infinite, because if you have zeros, right, 1 over 0 will be infinite. So what you do, you simply replace those infinite eigenvalues by zeros. That's it. So just to make it simple, if you have D1, D, T, and then 0, 0, 0 here, and I take pseudo inverse of this, this is going to be 1 over D1, 1 over D, I'll just call this T, 0, 0. So that's what it is for a diagonal matrix, and I leave it as an exercise to check that this works for arbitrary matrices which are symmetric. Okay, so in any case, this is, by the way, known as, I think it's called push through identity. Okay, so this is quite interesting because in a sense, it's the same formulation for over-parameterized and under-parameterized case, but in some sense it is not. And one thing which we can get out of this is the following. And let's think about the formula which I have here, like this, this star. So if you think about what this says, it says that W star actually lies in the span of Xi transpose. So star implies that W star belongs to the span of Xi transposed of the data set. So I want to say, usually it actually says that W belongs to the span of the data, but really it's not the span of the data, it's the span of the dual to that, because W is dual to the data. It's a technicality, but it's sometimes is important. In any case, that means that W star has the following form, right? Yeah, I can write it. W alpha I Xi transpose from I equals 1 to n now, right? Because I have n data points and it lies in the span. So I can write W star as a linear combination of my data points. And this is really important, and this is actually known as the representative. So probably not many of you have seen representative theorem written in this form, although it's actually the same as the usual. So I presume many of you have seen it for kernels. I'll get to kernels in a minute. But it's actually this fact. It's a fact that the solution can be written in terms of a linear combination of your data points. And this is really important because what does it mean? That means it's some form of duality. That means that W star can be found is, so instead of finding W star, I can find alpha star, which is simply argmin over alpha sum from I equals 1 to n sum, how does it work? Sum alpha I X I transpose X J, I should put J here, minus YI squared, okay? So this is an optimization problem of alpha. So instead of doing something solving over D, right, I can equivalently solve it over alpha. Now for kernel machines, this becomes extremely important. So you see I can change optimization over D and optimization over alpha. For kernel machines, the dimension is infinite. So there is no way I can actually do an infinite dimensional optimization problem directly. What I have to do, I have to do optimization in terms of the representative. And that was this whole foundation for kernel machines. So, so these are two different formulations. Okay, Tyler, question?
Hi. So I was wondering if this analogy you had where in the underparameterized case where you take an orthogonal projection of yi onto this hyperplane, does that not apply in the overparameterized case? And if not, is there a similar kind of analogy?
Yes, actually, and I should point this out. It's a really good comment. So in overparameterized case, I'm choosing solution with the smallest norm, right, in the span of this. And this is nothing else but the projection of the, so the smallest norm is the point which is closest to the origin. So it's nothing else but just taking the origin and projecting it onto the space of your solution. So this is orthogonal projection of the origin onto xw equals y.
See, but this is a different set to the hyperplane you were discussing earlier, right? Which was just xw.
Yeah, so it's not the same set, right? So if you look at the space of solutions, so there is a discontinuity going on. I think this is actually a really important difference between underparameterized and overparameterized. They're not the same. They look very similar in some sense, but they're not the same. In the underparameterized case, there are no solutions. In the overparameterized case, there are infinitely many solutions. So in the underparameterized case, you have this capacity control idea because there are no solutions. So you're controlling capacity by not allowing you to fit noisy data exactly, right? Because you cannot fit exactly, you just don't have enough free parameters to fit data exactly. In the overparameterized case, you can always fit the data exactly, but you have to choose which solution you use to fit data exactly. Okay? And geometrically, this is a very similar problem. Both are projections, but they're not the same projections. And the interesting thing is that there are these two ways you can write linear regression. So when you look at classical, books on linear regression, they usually don't deal with overparameterized case at all. They just have underparameterized. So you don't see this type of formula for linear regression. But once you realize you have to deal with overparameterized case, this is the thing you have to basically think about. Okay?
Thank you.
Okay, so next. So in general, linear regression can be solved in these two ways. In the original space of the W's or in this somehow dual space of alphas. So two ways to solve in alpha or in W. And depending on your exact situation, one may be better than the other. Okay, now let me just point something very quickly about optimization. And again, this probably is somewhat familiar. If you write optimization for gradient descent for this problem, and I'm not going to do the computation, but it's, you get something like this, WT plus 1. So this is gradient descent. WT plus 1 is equal to WT minus eta, which is the step size, X transpose XWT minus X transpose Y. Okay, this is how the linear regression works. And what you can notice here is that every update of WT is in the span of the parameters, is in the span of your data points. So every update, which is the same, right, is in span of data points of Xi transpose. So what does it mean? That means that your whole optimization path will be in the span, assuming it is in the span and initialization. So what we have, optimization path belongs to span Xit if W naught belongs to span Xit. And that means that if you start at the initialization within the span, specifically at 0, then you must arrive to the point with the smallest norm. So gradient descent converges to W star, which is argmin of norm W squared, squared x W equals y, assuming W naught is in the span. Notice 0 is always in the span, so if you start with 0, gradient descent guarantees that you arrive to the minimum norm solution. This is quite remarkable because this is this idea of the implicit or inductive bias, is that you just start your procedure at 0, and by default, it actually chooses your solution with some special property. Now, if you are not choosing W naught in the span, notice that there is a component which is orthogonal to the span. And because all of your updates are in the span, that component which is orthogonal to the span is never reduced. So the solution actually, so if W naught is not in span, then W infinity, which is the limit of gradient descent, will be W star plus W, let's say, I'll denote as W perpendicular, where W perpendicular is component of W naught orthogonal to the span Xi transpose. So you have this orthogonal component and it's preserved, so you have some sort of parallel transport when you're moving along. So there is actually an interesting connection here with if you don't have square loss, if you have something like a logistic loss, there is a way to reduce our component. About this now. But yeah, so somehow 0 is special. Initializing is 0 is special. Of course, you don't have to initialize exactly 0. You can initialize close at 0 to 0, and it will essentially do the same thing. So we will have a component, but it will be in general small. So there is a question: in what case would W not be in the span? Well, think about how how a neural network are initialized, right? You take some sort of random initialization. That is usually not in the span, but presumably it's not too far from the span either, right? Because your orthogonal component is going to be presumably relatively small.
May I ask what's the index I here when you're talking about the span?
I is just index of the data points. So it's a span of all my data.
Okay, so it's over all the data, yeah. Okay,
it's a linear combination of all of my data points. So the way to think about it, if you initialize, take an orthogonal projection onto, subtract an orthogonal projection onto the span, and that's a component which is not killed in optimization. Now, let me very briefly mention that SGD actually, SGD converges to the same as GD. So it's equal GD in terms of convergence here, which is quite remarkable because this is actually not true for underparameterized case. Underparameterized case, SGD with a fixed step size doesn't converge at all. It does. I'll discuss this later, but this is something which is different for overparameterized case. Okay, any Varun?
Yeah, I have a question. Could you explain again what you meant by like the dual of the data? I think it might be better for me to see like when you write the X matrix to get like all at once, what the columns are versus the rows, because then I can have like a bit like I want to like W star is supposed to have the same dimensionality of the data, right? So like, what do you mean by like the dual? Is it exactly just the data points?
It's just data point. Don't worry about it. It's a technicality. You see, W and X are actually technically different spaces because W is dual. But when we have inner product, we identify the space to its dual.
Okay,
so
that's
perfect. Why the dual here is represented by the fact that it's transposed, but it really makes no difference because we can.
It's
the
just
fact
like
that you can take transpose means that you have inner product essentially.
Okay, cool. Thank you.
Okay, so now, so this is I think, yeah, all I want to say about linear regression. Like 15-minute introduction to linear regression. Now, kernel machines. And I'm not sure how familiar everyone is with the idea of kernel machines. So I hope everybody knows. I mean, it's really a very fundamental mathematical object, which is known as a reproducing kernel Hilbert space, RKHS. And the idea here is the following. So first, I kind of do a very constructive way, then I'll say a few words about a more abstract way, or why, what happens, what we need. So suppose we have a kernel function. The kernel function is the following. It's just a function xz, k of xz, and you know x, z, I in rd. And when do we call it a kernel function? So we say that it's a kernel if it's symmetric. So k of x equals k of zx. We want it to be positive or non-negative. And we want it to be positive definite. Sometimes positive semi-definite, but I'll just assume it's positive definite here. Here, the interesting thing is that, well, okay, first, what is positive definite? And let me define this. So k of xz if pd, if for any xi I equals 1 dot n, the matrix k so this is a matrix kij equals k of xi xj. This is a kernel matrix. And I want this matrix to be positive definite. So k if pd, assuming xi is not equal to xj. So as long as xi is not equal to xj, k has to be a positive definite matrix. So I'm constructing this matrix, so think about what it looks like. K of x1, x1, k of x1, x2, and so on. So it's an n by n matrix. So this has to be true for any sets of xi. So this looks like a very strong concept. But actually, if you're familiar with positive definite, right, a matrix, if you have a positive definite matrix, any minor of that matrix is also positive definite. So if you think of the kernel itself as a matrix, right? What is a matrix, right? Matrix, some sort of table. This kernel function itself is like a table, except it's indexed by real numbers. Now, each one, when you select those data points, this is selecting rows and columns in that infinitely large matrix. And what I have here, the kernel matrix, is a minor of the kernel function. So this is to say that every minor has to be positive definite, every finite minor. Okay, so that's what the kernel is. Now, if K is a positive kernel, we can construct the following inner product. So inner product, which is KXI dot. So what do I mean by this dot? I just mean that this is a function of that argument. So open argument. So it's a function, right? I'm fixing the first argument of a kernel, but the second I'm leaving open, so it's a function. And I'm constructing inner product between these two functions using the following equation. So notice this is an inner product, and I'll put K here to make sure that this is a different inner product. This is a product of two functions, right? It's a functional space. And the product of two functions is this K of xi xj, which is a number. Now that's basically the definition. And what is RKHS? RKHS, you take this points as a basis. So you can now complete, you can now take any linear combinations of those functions and extend this. So if you have sum alpha A, alpha I K of xi dot, and sum beta j K of, let me call it z j dot. Okay, these are all functions of this type. Then the inner product of this is going to be sum alpha I, and this is sum over I, and this is sum over j. Alpha I j, alpha I beta j, K of kxi dot, kzj dot. And this, using the formula that I just have, is simply going to be sum alpha I beta j, K of xi xj. Okay? And this is not x, this is c. No, that's how it works. This is the inner product. Now, okay, I'll leave it as an exercise to prove that this is actually a valid inner product and it satisfies all the properties that we expect from inner products. So this space is an RKHS almost. What is missing from it here is that this space is actually not a Hilbert space. And you know, if you remember, Hilbert space needs to be complete, meaning that every Cauchy sequence must have a limit. And if you look at this space, it's not complete. So what you do, you need to do the completion. So take this inner product and complete. So taking limits of this finite linear combination. And then you get RKHS with kernel K X Z. Okay, so that's so what is a completion procedure? It's essentially how you get real numbers from rational numbers, right? What's a real number? A real number is nothing else but a Cauchy sequence of rational numbers. What's a Cauchy sequence, right? It's the sequence whose differences become smaller. You can do in similar ways using what is called Belkin dots and so on, but it's essentially the same thing. So there is this completion procedure. Okay. Now, it's a very good exercise to actually go through it and construct it yourself to make sure that you can prove all these properties, because obviously I'm spending 5 minutes on something which requires maybe 10 pages of a book to actually do this correctly. Yeah, somebody had a question.
Yeah, this might be obvious if I think about it a little more, but it isn't to me right now. Is it clear that the completion, like, obviously consists of functions? Because right now we're just kind of defining it as like an abstract object that's the completion in this Hilbert space.
Yeah, so the completion, I don't want to mislead. I think you essentially need, I think maybe you need K to be continuous. I don't know, I don't remember the exact condition, but basically under some very mild condition on K, this will be functions, yeah. But
Yeah.
you're right, if you just do completion, right, you get some sort of abstract.
I mean, I suppose with L2, you actually don't get functions, you get like equivalence classes of them.
This is very good. L2 is not a reproducing kernel Hilbert.
Yeah.
Yeah.
So here, do you actually get like functions defined everywhere?
You get functions defined everywhere, yes.
Okay.
Under some very mild, actually there may be even no, like maybe you just need K to be pointwise defined. So I'm not sure. There is a reference in the slide, you could check exactly. There is actually a very nice old paper by Aronstjan from the 50s, who actually was the guy who introduced RKHS, who very nicely does the construction, everything.
Thanks.
Very clean.
Maybe I can make a remark, Misha. One thing you can do if you want to derive various things is you can expand things in the eigenbasis of K. K is a symmetric, positive, definite thing. So it's got some resolution of the identity for it. And, so if you know that world of things, that's another way to like convince yourself that certain things actually make sense.
Thanks, Boris. Yeah, that's another way is to look at this whole, yeah, so that's kind of a complementary way to look at it. You can look at the operator given by K. Actually, there are some many interesting properties of looking at this as an operator. I will not discuss it. I'll give it time constraints, but let me give you actually another definition of RKHS, which is more abstract, but connects maybe better than, but it's better maybe with things that we want. And RKHS is simply the following. RKHS, equivalent definition. Consider a Hilbert space of functions. Hilbert space of functions. So any Hilbert space of function that you want, but they have to be functions, and just assume they are on RD. They don't have to be, but to make it a little more precise, more specific. And consider evaluation functional. So the evaluation functional is the following. It's a functional phi of x. So phi of x of f is equal to f of x, okay? So it's a functional which evaluates my function at a point, okay? And it's obviously a linear function. And here is the claim. So Hilbert, I'll call this Hilbert space H. So H is an RKHS if phi x of f is less than c times norm f. In other words, the evaluation functionals are bounded. So this is very interesting because this looks like a purely abstract definition, right? There is no kernel, nothing. Surprisingly, just from this, you can derive kernel, and you can, by some, actually it's not difficult, you just take some dual to the functional. But it's very nice that from this purely abstract definition, you could derive all properties of kernels. Now, why is this a very nice definition, aside from the fact that it's clean and simple? Right, so it's clear what it means. So this is for all f, phi x of f is less than c of f, c times norm f. So you cannot have something which has small norm take a big value at a point. And why is this important? Because think about L2, for example. L2, you can have a function which has 0 norm, right? So you just take function 0, you change it to be some huge value at one point. That doesn't change the norm because, you know, L2 is not sensitive to changes at one point. So nothing like that is true for L2. You need some sort of smoothness. This forces you to be somewhat smooth. And that's actually what we need. Because think about what we need in machine learning. What do we get? We get observation at single point. And from those observations at single points, we want to deduce something about the function which produces them. And if you think about it, this is perhaps the most natural condition for a connection between observation at a point and some structure of the function itself, as represented by this norm. So that's why it seems that this formalism of reproducing kernel Hilbert space is a very natural way to think about it. Yeah, any questions about this? This is, I think, an important conceptual issue. And questions? No. Okay. And then
I was actually kind of curious. What, given the evaluation functionals, is there sort of like a easy way to see what the actual kernel would be in terms of these?
And not so simple. So what you do, you represent, so there is what is it called, Banach representation? There is some representation theorem which says that a bounded functional can be represented as an inner product.
Oh, it's okay. Like the Riesz representation.
Riesz representation, yes. Okay. And you just use the Riesz representation theorem, but you say, okay, what is a function that represents X? And that actually one half of the kernel, it's K of X dot. That's a function. That's how you define the kernel.
Okay.
You use Riesz representation theorem to the evaluation function. And then you kind of unfold this whole thing and you get everything. Okay, so that's basically how this works. But now let me sort of give you the upshot because I'm running out of time for this. So notice, for example, that L2 is not one of these, right? And you have to have functions which are actually pointwise defined for one thing. Makes sense to talk about evaluations. So in L2, you can say, okay, not really, evaluations are not really defined. Certainly not bound. Okay, so now what's the upshot of this? The upshot is actually quite beautiful, is that you can solve the problem that we kind of want. So if we think that this is a structural norm on the function, that good functions have low norm in this RKHS space, and that can be made actually precise. So for example, in some cases, they're equivalent to Sobolev spaces, just controlling the derivative. Some Sobolev space RKHS. Then we can think about, let's just do what we did for linear regression, and except that we're doing all of functions. And so consider F star to be argmin over F and H of norm F squared in H, such that F of xi is equal to yi. Okay, that's an analog of linear regression in the overparameterized case. Then the claim is, so claim F star, and this is known as a representative. F star is equal to sum alpha I k of xi, so from I equals 1 to n over my data points, k of xi x, and moreover, alpha I and the vector of alpha, so is equal to k to the minus 1 y, where k ij is simply equal to k of xi xj. And I'm sorry that I'm denoting the kernel and the matrix by the same letter. Well, think of one being like a big K, the other big small K. Okay, so this is remarkable, right? Because think about what is happening here. Is that I can minimize a functional norm of my data points. In principle, this is some terrible infinite dimension. So if I just give you a functional norm and ask you, what's the smallest functional norm function which fits my data? In general, there is no hope, right? It's some horrible variational problem. In this case, not only there is an explicit solution, but a solution whose coefficient can be found by matrix inversion. And actually, this relates directly to the discussion that we had before. This is equivalent to having some feature map in the infinite. It's equivalent to linear regression in the infinite dimensional space. It would take some time to explain exactly why, but it's equivalent to what we discussed before. It's solving in terms of the alphas is like solving in the alphas for linear regression. It's exactly the same. So that's the kernel machines. Usually, what people usually do, they do this kernel ridge regression, which is actually this. F star, and you can put lambda here is equal to argmin f in h of sum f of xi minus yi. I'm using square here. You actually don't need to use square. You can use essentially any loss, but it's simpler. But so this is ridge regression, and the same thing holds. So f star lambda equals sum alpha I k of xix, and alpha I equals k plus lambda I to the minus 1 times y. And this is vector of y's. This is not alpha, this is the vector of alphas, sorry, of y's. We will not talk about ridge regression so much, but this is kind of typical way it's been used. When lambda goes to 0, ridge regression becomes so f star lambda, if lambda goes to 0, goes to f star. That's another way to define pseudo inverse. Actually, you can write it as you can have a little ridge, go it to 0, and take the inversion. That's an equivalent inversion. Okay, I should probably stop here, and I'm more than happy to take any questions. And
yeah, thanks, Misha. We have plenty of time.
So I have a question. It's kind of general, but so I wonder, like I guess in practice, not always maybe, but in many cases, you're not exactly ever interpolating. You always have some kind of epsilon error or something. And I wonder, like, how does it affect like qualitatively any of the results you're talking about, like, or is it like like a ridge with lambda going to lambda being small, or I mean, is it an important detail, or is it just gonna be not so important?
So it's an interesting thing actually, because at some point I was looking at some of the results on kernel machines which usually used ridge. That was a typical formulation. Actually, SVM is kernel SVM, which many of you probably know. It's equivalent formulation that, except for the square laws, you're using the hinge laws, and you're still using ridge. And ridge was equivalent to this. What is it called? There is a parameter C. I forget what it's called now, but it's actually equivalent to the ridge. It's just 1 over ridge with the hinge laws. In any case, you look at what people used, what kind of parameters were people used in practice. And then you realize that they took value of lambda to be something like 10 to the minus 8. So yeah, it's rich.
No, but I wonder like for a neural network, so you train it and it almost interpolates, but there's some kind of residual noise, either from if it's stochastic gradient descent, or either you just you stop it with some tolerance parameter, and it's not ever exactly like zero training loss. So I wonder if this residual is somehow important, or is it, not so important?
It may or may not be important depending on, so some of the experiments I showed before in the previous lecture, they were actually for lambda being exactly 0. It's exact inversion. In practice, and it works still fine for most cases, not always, but no. In practice, it is often does make a difference that you do early stopping, you get a slightly better result. So there are two reasons to do early stopping. One is that you often get, not often, but not always, you get a slightly better result. Second, sometimes significantly better. Second is, of course, you're saving computation in practice. So you even if it's not better, you still want to stop. The thing is, so from a practical point of view, I think there is really no reason to do interpolation exactly, because you are not getting anything extra and you're probably using more computation. However, from a theoretical point of view, you see, that's why this idea of a prism is that you have, it's a very clean setting, because what you're saying here, if you look at, where do I have the, so you look at this condition, right? F of xi equals yi. That's an exact condition. So you can analyze this very precisely, because this is very precise. Once you're allowing some slack, how much slack, how does it trade off with the kernel? There are suddenly like 10 different questions that you can ask about, like the same as reach, right? How exactly do you choose reach? When is the value of a reach optimal? These are all very interesting questions, but they're complicated. You can solve them in specific models, like maybe for Gaussian distribution or something else. But it's very difficult to get some sort of general answers to this. And what we know is that in practice, it's probably not that important to have lambda to get at least good performance, maybe not very optimal. So removing this, I think, conceptually simplifies a lot of these issues. It gives us a better kind of theoretical handle on what is going
on. If no one else, well, I have a question. It's, so the kernel that we see here, like in the context that we'll care about for deep learning, the kernel will end up being the neural tangent kernel?
In
some cases?
Potentially, yes.
Okay. The reason I bring that up is you were saying that once we have the kernel, and we're gonna, using the representer theorem, whenever we do optimization, our solution will be able to be represented as like a linear combination of the kernel, like evaluated at points, right? So the thing that I guess maybe is a question that will be answered later, is while you're doing gradient descent though, for neural nets, the neural tangent kernel, like it changes, right? Because you're changing the parameters. So I guess like in the case that we're going to be looking at, is the kernel sort of changing as we go along, or how is that?
So one of the remarkable findings has been, is that in some regimes, which is actually a reasonably good class of regimes, it doesn't change. It's actually neural network is mathematically equivalent to kernel machine along the whole, like in a whole neighborhood which connects the solution. So we'll discuss this in more detail, but this was to me was a kind of a shocking discovery.
Oh,
I have argued that kernel machines are similar to neural networks. It turned out they're actually the same in this regime.
Are you saying like it's like while you're training it, like the kernel that we actually have for the neural net is like either like the integral over like as you take step sizes, like if you of like an integrated kernel of sorts, maybe, I don't know. It's like some, because I read a paper like that.
No, it's literally, okay, how should I say it? Literally, the theorem says that for a broad enough neural network with, essentially for any wide neural network with a linear last layer and a certain initialization, what's called NTK initialization, the output of the neural network in training is the same. Actually, the neural network is actually a kernel machine. It does the same thing. It's a kernel machine.
Okay. Okay.
Which
Cool.
is, I think it's a totally amazing result. I think it's, yeah, only discovered with three years, like about 3 years ago. Yeah. So Yaida, I see you. Yeah.
Yeah, if I can please ask a question. So in general, I'm wondering about the why we're looking for the minimum norm solution, both in the linear case, the linear regression, and in the kernel case. So I'm imagining the three graphs you had before, and the two last ones, they're both interpolating, right? But I don't understand why like the second one would have a bigger norm than the third one or something like this. Yeah, in this.
Yeah,
exactly.
So you see, in the classical regime, right, there is no interpolating solution, and this is the minimum. This is the best fit solution that we have, right? For this one. This is best fit. Now, when in the modern regime, we have to choose somehow. And what does linear regression do? It actually just chooses minimum norm solution. So in some sense, there is a kind of unhelpful answer. I guess we choose it because that's what linear regression does by default somehow. There is maybe a better way to think about it, is that really, what would we choose, right? We have an infinite space of things, right? Shouldn't we choose in some sense the simplest one? And the simplest one, you can argue that this is the one with the smallest norm. And what is the smallest norm? Well, think about linear regression, it's just a slope. Norm is just a slope. So we somehow want to choose a solution which has the smallest slope. So if you know about this maximum margin type of thing, that's exactly the same idea. So it makes some intuitive sense to choose something which is minimum norm. Think about functional spaces. If you have the functional spaces are very, very rich, right? They're dense in L2. So any functions can be approximated, but do you want to approximate it with something which is nice, or some crazy oscillatory thing which does some stuff? So these are not maybe completely convincing, fully convincing argument, but there is not really much alternative in a sense. Oh yeah, and there is a third thing. Let's think about what gradient descent would do, right? If you start with 0, which seems very natural, gradient descent would give you the minimum norm solution that we have discussed. So there is some sort of, it's not, there are two standards of trial, right? There is in the US, there is beyond reasonable doubt, which is for criminal trials, and there is preponderance of evidence, which is for civil ones. So this is preponderance of evidence rather than beyond reasonable doubt.
Right.
Thank you for this question.
If I can add a small follow-up question. So just looking at these, so when you described it, so the second frame is clearly not good in some sense, and then in the third one you say, okay, it's a nice smooth curve that sort of fits. So wouldn't you want, like, I don't know, to minimize some norm that that represents smoothness or something like this, not necessarily the L2 norm?
Yeah, so I would like actually, so this is not L2 norm, this is some other norm, this is a kernel space actually. So this is some splice and splice correspond. So what I would like actually, I would like something more spiky than this because of the discussion we had before, that spikiness is actually good for this. This is not spiky enough because if you add a lot more noisy data, you will see that it kind of starts going all over the place. However, and this is we don't see in this picture, what it seems to be that in high dimension, even this is sufficiently spiky because of this blessing of dimensionality. Even norm like this, even something like a Gaussian kernel, which is very, very smooth, in one dimension, you cannot even fit noisy data with a Gaussian kernel because you get numerical issues. The matrix, even though it's positive definite, it's very close to being degenerate. The eigenvalues are very small. But in high dimension, even that works okay because somehow you have some sort of blessing of dimensionality there. So it may be that it's not so important to have spikiness in one dimension seems like too crazy somehow. Okay, so I see there are several. William?
Hi, yeah. I was wondering, we define a pseudo-inverse matrix by either through this like optimization procedure or through, you were talking about how you could do ridge regression where you take the lambda parameter to 0. I was wondering, is there, if you define another norm, like just take the L1 norm instead of the L2 norm in the ridge regularization and take lambda to 0, is there an equivalent matrix that pops out, or is it somehow harder to compute?
Well, so actually, if you look at the sparse, there has been a big line of research on this compressed sensing that's essentially taking a kind of pseudo-inverse for L1 norm. And then you can prove certain things. Although I think they still usually don't fit the noise, but I think there was recently some work when you can fit the noise as well and get good results. But yeah, basically you can prove that if you do something like a pseudo-inverse, but with L1 norm, you can reconstruct, if the signal is sparse, you could actually pick out the coordinates which have signal. That was a very significant line of research, in particular, became popular about 10 years ago, 10 or 15 years ago.
Okay, thank you.
More like 15 years, 15 to 20 years ago. Christian?
Hi. I was about to ask, can you relate the interpolating KNN schemes that you talked about last time with the idea of smoothness? But from your comment to the previous question, maybe I'll modify my question to, can you elaborate on the blessing of dimensionality for, let's say, the Gaussian kernel and like spikiness? In some sense, I don't see how things will get better in higher dimensions.
Yeah, so there is one way to actually think about spikiness for the Gaussian kernel, okay, that requires this would require developing some more intuition, but I can just say those things. So you see, Gaussian kernel in one dimension. If you look at the Gaussian matrix, kernel matrix, you will see that it has very quick decay of the eigenvalues. And the fact that eigenvalues decay quickly actually corresponds to smoothness. So somehow smoothness is a decay of eigenvalues. So if you look at Sobolev classes, if you want, say, 5 derivatives, that means that the eigenvalues will decay something like 1/n⁵. So for Gaussian kernel, it's actually exponential decay. So you get very, very quick decay in one dimension. Now, in higher dimension, you still get somewhat exponential decay, but it's actually slightly sub-exponential. It's something like, instead of having e to the, so i's eigenvalue being e to the minus I, it's e to the minus I to the 1/d, so d's root of I. That's still pretty quick, but when d is large, you see that the spectrum is actually flattening out. Because you know, if d is like 1,000,000, right, then it's essentially, the spectrum is constant. So what is happening is that in high dimension, even something like a Gaussian kernel becomes having much more flat spectrum. And this flat spectrum corresponds to somehow requiring less smoothness. And that's a blessing of dimensionality considered in this one way. That's some sort of manifestation of the spikiness. That's why this nice smoother kernels in high dimension also do okay when you interpolate. So
Thanks.
that's basically it. Yeah, Friedrich?
Yeah, so this is maybe kind of a follow-up to Ido's question regarding the minimal norm. So this also has to do a lot with how you parameterize the problem, right? In a sense, what kind of model you choose. I mean, I'm kind of trying to get this straight in my head. Like when you think of let's say, fitting a polynomial, for example, you could choose your parameters to be ax to the ap x to the p or something. But you could also choose a over k factorial, like in the Taylor expansion, or you can maybe divide by the range of that your data comes from, and this will all give you different solutions, right?
Yeah, so definitely it's parameterization dependent, and how should I say it? It's definitely you can find some really weird parameterization which would do something strange, right? It's not hard. On the other hand, it seems that when you have some sort of natural, so think about Fourier harmonics, right? There is some sort of natural parameterization by smoothness, which relates to the frequency of oscillation. Fourier, right? Mm-hmm. The less it oscillates, the nicer it is, and this corresponds to eigenvalues of the corresponding operator, like so there is some sort of natural parameterization of smoothness, and it seems when you follow something like that, you generally get at least reasonable answers. So okay, maybe there is a way to reformulate this a little bit. Think about what do we expect from functions which happen in the real world, right? You know, if you play chess, when you move one piece, like a position with like, imagine you're moving like your king under check, or you're moving your queen when it can be taken, right? Just one small move can make a huge difference. So it's somehow discontinuous with respect to the pixels which are positions of. Now, if you look at an image, well, changing one pixel doesn't do anything, right? A cat doesn't become a dog because of one pixel most of the time. So I guess the question is, what do we expect from natural images? And we expect some sort of smoothness, and this smoothness manifests by like, okay, changing, if you have a sensor, probably in most cases, measuring temperature here, measuring temperature there is not really going to make any difference. So that's why parameterizing it in a way which respects smoothness seems to make a lot of sense. And that's what this RKHS do for reasonable choices of terms. It's essentially like Sobolev space. So you can think of RKHS as having some sort of smoothness parameterization, Sobolev space type structure, but having this amazing property that you can compute the solution explicitly.
Okay, so in a sense, you would expect that if RNNs, or not RNNs, but if neural networks do well on generalization, then in some sort their parameterization, even if they're in the linear regime, like in the kernel regime, then they still, it's smooth enough in a sense. So it's kind of a,
especially in the kernel regime, right? Because in the kernel regime, you actually know that corresponds to kernel, and that kernel is some sort of Sobolev like Gaussian, whatever, Laplace type of thing, right? So this is great.
Yeah.
So this actually gives us somehow more evidence that this is happening.
Yeah, I mean, I guess in the case of deep networks, you can then kind of choose how much each layer is contributing to this, for example, right? So you have all these kind of, just wondering whether there's any guideline towards a more proper, like a more well-behaved initialization over others. Parameterization, that's the word, not initialization.
Yeah, that I think we don't have that precision yet in thinking of this. I mean, I presume there should be, and it has to somehow connect with what we expect from natural data. Oh yeah, I should point out, when you're interpolating, everything is data dependent, right? Because you can break any, if you're trying to do the smoothest solution on a chessboard, you're not going to do well, right? It has to be data dependent, right? There is no uniform bound of all possible probability distribution. So we have to worry about what actual data look like, which I think that's how people learn, right? When we are data dependent, right? We somehow our ability to predict our inference depends on the inputs. You know, children learn how to do certain things.
Okay.
So, but yeah, I think that's hopefully in the future, once we get a better understanding of it, we will be able to use it as a tool to actually select specific architectures.
Okay, thanks.
I see there is I'm not sure how to say that. Selen or Kellen?
Yeah, that's me. So my question.
How do you say your name?
Kalen.
Kalen.
Kalen, yeah. So my question was, I understand that for the kernel regression and linear regression, we choose the W star that's the minimum. But when we're training the neural network, we're not explicitly choosing the minimum norm function. So I was wondering how this process manifests itself in that the function that ends up being chosen is the one with the minimal norm.
Mm-hmm. So let me make a couple of points here. First, we don't know for neural network that the function which is being chosen is minimum norm. It's some sort of reasonable hypothesis that something similar happens. And why is it reasonable? For the following reason. First, if we have a linear regression, right, which is a special kind of neural network, then we actually know that it's minimum norm. And by linear regression, I mean something like kernel machine as well, because that has the same properties, although it's of course non-linear function. So we do have a nice class of inference methods which actually do have this property. That's one. Second, we know that in the infinite limit of neural networks, we also have this property, because that actually, I'll discuss this more, but that actually becomes kernel machines in some limits. So that's two. Three is that even when we know that it's not a kernel machine and you can see that the kernel is changing and so on, it does look like solutions of neural network have a lot of regularity and some sort of smoothness in them. So it looks at least that it's reasonable to think it's some sort of minimum norm solution. But we don't have a general theorem saying that, okay, it's always a minimum norm solution.
I see. And this may be a naive question, but basically it's based on the kernel regression itself, we find the minimal norm solution. It's not a choice to select in the overparameterized regime. You said that there's infinitely many solutions and we select the one with the minimal norm, but that's a product of the kernel regression, or we choose the one with the minimal norm, right?
So it depends, right? In principle, we can choose any solution, but if we do something like gradient descent and initialize it at 0, then we don't have that choice, because the stochastic gradient descent will choose that solution for us.
I see.
But in principle, of course, it could be anything, right? So theoretically, I mean, in principle, there is this infinite space of solutions. But that's perhaps the one which is most natural, and moreover, it is the one which is chosen by optimization method that we use, which we know work. And there are other theoretical reasons to also look at minimum norm solutions. So we know that at least, okay, maybe I should put it like this. We're pretty confident that the best solution is not too far from the minimum norm solution, even though it may not be exactly the minimum.
I see. Thank you.
Any other questions?
Maybe I could ask just one other quick question. Could you quickly go over, or maybe there's not enough time now, but just how is it that the gradient update remains in the span? You mentioned that in the gradient descent that the update remains in the span, and that we would understand when we use the NTK that by the fact that the gradient update remains in the span, we can then solve the kernel regression.
So for NTK, it's a little bit more tricky than that, because there is also some initialization. But yeah, I don't have, unfortunately, time to go over the actual computation. But if you look at the formula, you will see that the update itself for linear regression, it's something like X transpose times something. And when you multiply X transpose by some vector, right, that's in the span of the rows of rows or columns. Okay, I can never get this right. Of X transpose. So if you actually just look at the expression which I had in my notes, then you will see that it is a span. Now, one interesting thing I would like to add is that when you have stochastic gradient descent, it's actually also in the span. So with a gradient descent or stochastic gradient descent, it works the same way.
Right. So maybe let's take the rest of the questions offline, just so we can stay on schedule. But thanks a lot for the very nice lecture, Misha.
Thanks, Boris, and thank everyone for great questions.
Yeah, definitely. You know, there's going to be another TA session. I already mentioned that earlier. So you can obviously ask the TA for this course, or, you know, maybe ask directly on Slack or whatever.
Actually, yeah, that would be. Oh yeah, before I stop, I would like to point out this reference, which is a very nice reference on RPHS internal called by Holger Wendland, Scattered Data Approximation. It's a book.
Yep, thanks, Misha. If you're there, Sho, you should feel free to share your screen when you are ready.
Great, I'll do that now.
I cannot oh.
Oh, there we go. Excellent.
Full screen, I suppose. And
yeah, we can see your cursor,
cool.
everything moves, everything's great. Okay. Yeah, well, so we're to have you back for lecture 4, Sho. Take it away.
Okay, we don't need any rest, I guess.
No rest for the weary.
Okay, that's hardcore. Okay, so this is lecture 4 of the series of the lecture that Dan and I are giving. And in a previous lecture, we covered the principle of sparsity. And in this lecture, I'm going to cover another principle, which is the principle of criticality, as I advertised in the last lecture. And please ask questions and yada, yada, yada. Okay, so the review of the last lecture, the principle of sparsity for wide neural network. So we began this lecture series with the goal that we want to go from the initialization distribution for the model parameters and then the microscopic description of the network at initialization, and then pass on to the statistics at initialization, and then further go to the statistics after training. So that was the whole goal. And what Dan has covered in the first 2 lectures is that he has established basically the map from the second to the third, assuming that there is a sparsity in the description of the neural network dynamics. Namely, that Dan has studied the linear model and the quadratic model and expressed the free train solution in terms of the quantity at initialization, like G hat and NTK and DNTK. And what he has done can be extended to cubic model, as we have done, and well, in our privacy, and we can do it to a higher order. So assuming sparsity, you can always solve the dynamics in a closed form using perturbation theory. Now, like what I've done in the last lecture was to complete this map by looking at the map from the first to the second, meaning that I started with the model parameter distribution at initialization, and then I mapped onto the statistic of the object that we care, like the network output, NTK, and DNTK at initialization. And in establishing this map, what we found is that this distribution in the middle simplifies a lot when you take a wide neural network. And in particular, if you take a infinite width limit, then this distribution in the middle is described by just 2 numbers, or like more generally 2 matrices. So one of them is specifying how the network output is distributed according to Gaussian distribution, and G is the Gaussian covariance of the Gaussian distribution. And H is dictating like what the deterministic frozen NTK is at initialization. But this was too simple to describe the realistic neural network because it's just a linear model in disguise. So we back off this limit and went to the higher order infinite width expansion. And at the 1/n, so where n is the number of neurons in the hidden layer, we've found that still like this distribution in the middle can be truncated at the finite order. So but now we have to consider network output, NTK, and in addition to them, we have to include DNTK and DDNTK that drives the representational learning of the model and making the dynamics more nonlinear. And then like in this case, you have more letters to keep track of, like G, H, V, ABDF, PQ, RSTU, but it's still a handful of the numbers or tensors to specify the distribution you care. And to remind you, this G and H and so on can be obtained by some recursion relations that I'm going to flash later in the talk. And one thing I didn't know last time, but then it kind of came to my mind over the weekend, is that like there's different notion of sparsity in the literature, and I wanted to distinguish our notion of sparsity from that. And for those of you who knows like lottery tickets hypothesis or the pruning network, there are like people try to prune the network by sparsifying the network by truncating the model parameter that you don't need. But here it's the different notion of sparsity. Like we're not talking about the sparsity of the network itself, but the sparsity in a description of the network, which is fully connected and everything. Okay, so this is a caveat that I wanted to lay out just in case. Okay, so in the last lecture, to be more specific, like we covered the principle of sparsity and we derived a recursion relation that determines this object that governs the distribution. In this lecture, I'm going to switch the gear. And so in principle, that recursion determines the statistics at initialization fully, and you could solve those recursion by numerically as well. But then like what I'm going to try to do today is to analytically solve these recursions so that we can understand what the deep dependence are, like what is the deep doing in a deep neural network. And this is not just a theoretical endeavor, but we will be rewarded by some practical lessons. So as we go along today, like we will try to see how to avoid this exploding and vanishing gradient problem for deep neural network that has plagued the applicability of neural network in early days, but now there are many cures, but then we have a systematic way to avoid these problems when they arise. Okay. So that was the review of the philosophy, so to speak, of the last section and where we are going today. But let me review more details. So like now, first review the notations of conventions. So first, like these biases and weights in the neural networks are initialized with the means of Gaussian with some variance. And for example, CB governs the variance of the biases and CW governs the variances of weights. And importantly, these CB and CWs are called initialization hyperparameters to distinguish them from the model parameters. Also, they are dictating the initialization, so the name. And one important aspect is that we are dividing initialization distribution for weights by 1/n, the number of incoming signal to the neuron in that layer. And similarly, this diagonal group by group learning rate. So in Andrea's talk, again, this was called S matrices, but for us, like we call that lambda. So it kind of does let you control how the model parameter gradient in the model parameter theta mu affect the update in theta mu. But in practice, we'll just use it to dial the amount of the learning for each group of the parameters. So like for biases, we scale by lambda mu, lambda d. And for weights, we scale by lambda w divided by number of incoming signal. And again, this 1/n effects and factors are there to ensure that the NTK and the distribution of the pre-activation, both of them behave nicely when you take a large but finite when you enter the large width regime. and CW and lambda W are order 1. And finally, two pedagogical simplification I made was that I'm going to focus for these lectures for a single input so that I can drop the sample indices. And also I'm setting this hyperparameter to be layer independent. And I'll stay true to that, except one slide where this layer dependence could be beneficial and important. So I'll indicate where they are important. Okay, review of strategy. So like with this node, well, set up, and we try to follow the distribution of this object from first layer to second layer to third and fourth. And we, in particular, like did the first layer, studied the first layer distribution in detail, and it was like NTK was frozen and deterministic. DNTK and DDNTK all vanished. And in the second layer, in a finite width effects kick in, and they get the 1/n corrections. And these guys are recursively amplified as you go deeper in the network. And we have some recursions. So let me review some recursion that dictates the transformation of distribution as you go deeper in the network. Okay, hopefully this is just a review, but please do ask questions if this is too fast. Okay, so now, review of some recursions. So we, in particular, looked at the statistics of pre-activation or the network, well, yeah, pre-activation in the hidden layers. And this is basically the norm of the pre-activation in a layer. And this Z followed the following recursion, where Z in the L+1 layer is given by CV, the initialization hyperparameter, plus CW, another initialization hyperparameter, times this Gaussian expectation. So Gaussian for single neurons. So here, like the leading order contribution is given by single neuron expectation or single variable Gaussian expectation, because every neuron didn't talk to each other at leading order. And there's 1/n corrections that you can compute, but in this talk, I will just suppress them. There's another 1/n effect that's more important. Similarly, you can do the same for the NTK mean, and so NTK is H, hat is to indicate the initialization, stochasticity in the initialization, and expectation of that is given by this, and it follows the recursion relation as such. And again, I'm truncating 1/n. And sort of finally, this is one of the important finite width effect was this 4-point connected correlator, or there's a non-Gaussianity that appears at finite width effect, and this amount of the non-Gaussianity is captured by some recursion that I flashed last time. Okay. So these are like, if you don't remember the last lecture, you can just take them as an axiom for today's lecture. This is what we are going to solve today to get glean some insight into how the deep neural network behave. And one more thing. So today I'm gonna just look at the leading order effects in each of the recursions. So like I'm gonna look at, so this Z in principle have its own 1/n expansions, but I'm gonna just keep track of the leading order contribution, which is called K. And it follows this recursion from before, but I'm just like throwing away 1/n corrections. And it's a closed recursion. This can also be interpreted as the infinite width limit of this object. And there, people usually talk about the Gaussian process kernel, and this K is that object. And this is customary notation. And similarly, NTK mean can be expanded in 1/n, but you can look at the leading order contribution, which is customary denoted sometimes, at least, as capital theta to distinguish from the model parameters. And it follows this recursions. And then finally, the V, I'm going to just throw away 1/n square effect because it's small. And just keep the leading finite width effect as such. Okay, many more things. I didn't show it last time, but then for completeness, just to show you that they exist, these are the recursion that dictates how all the objects that I stipulated behave like A and B and D and F are governing the fluctuation of NTK, and P and Q are D and DK, which is responsible for the representation learning, and the RSTU or DD and DK, which is responsible for the movement of the D and DK. But this is just for completeness. I'm not gonna explicitly solve this in lectures, but I'm gonna show you only the results of the solution. Cool. So that was the whole setup. So I'm outline of the rest of the talk is following. So I'm going to try to first study the what's called scale invariant activation functions, such as linear function, the activation, ReLU, leaky ReLU, and such. And since they are actually pretty simple and they respect some special symmetry that we can just solve them analytically pretty easily, even within a lecture or half a lecture. So, and then from them, like we're going to attain some analytical insights into how the depths amplify some effects, and then how some of them we should tame, and how to tame them. And in the next part, I'm going to talk about more general activation functions such as tanh, sine, JELU, switch, perceptron, sigmoid, soft plus, and so on. But there's a unified framework to talk about all these things. So that's the scheme of which I'm going to describe, and I just apply to this bunch of activation functions. And then third, like I'm going to talk about how the finite width effect grows in a deep network. And then I'm going to end with a few remarks on like why criticality is so important for deep learning. Okay. So far, so good. Scale invariant activation functions. So these activation functions are given by following equations or defined by following equations. So sigma z is defined by, for the positive axis, a plus times c, where a plus is some constant. And then on the negative line, you have a minus times z. And for example, just like it's easier to understand with examples. So if a plus and a minus is equal to 1, that's just linear functions. Yes, and then in contrast, if you put the a plus equal 1, but then set a minus equal to 0, that would be ReLU functions that you all know about. And then you can do something else. For example, like leaky ReLU is given by slope 1 on a positive side line, but then another smaller slope on a negative side. And then usually people pick 0.01, but then I here picked 0.1 so that you can see it. Okay, so let's solve the recursion. Let's start with the kernel recursion for this activation function. So this where I just copy and pasted the definition of k, where they come from, and this is k is the recursion that this kernel follows. Okay. So to work with this recursions, we have to first evaluate this Gaussian expectation for this kind of activation functions. So first, like this is just a definition. So sigma z is Gaussian integral of sigma z. So that's that. This is the first factor is normalizer. And then so like now let's just plug in how all those activation functions. So on a positive axis, what you get is basically a plus z square. So you have this guy and that guy, and just I pull off a plus square in front of the integral, because that's constant. And similarly, on a negative line, what you have is a minus square g square. So that's that. And I pull off a minus square in front. That's easy. The only non-trivial step in this kind of trivial algebra is the following. So you notice that this integral, the integrand is even function. So it doesn't matter whether you integrate from 0 to infinity or minus infinity to 0. So you just add them up and then divide by 2 just to account for the doubling of the integral range. And similarly, you can do the same for the second integral. So you extend from minus infinity to infinity and divide by 2. Okay, so that was sort of non-trivial, but trivial. And next, like you notice that these integrals are just same for both of them. So you just pull out the common factors as you do in elementary school. Now this integral is just Gaussian integral of g squared, which is just k. So you get this. Okay, so that was trivial algebra, but then it's good to kind of feel confident by doing such a simple algebra. Okay. Now, so the result of this calculation is that the Gaussian expectation of sigma square is A2 times k, where A2 is defined by this equation, and it's given by some constant that dictates the activation functions. For linear activation function, this would be 1, and then for ReLU, it would be half, and so on and so forth. Okay, so now that we have evaluated the integral, let's plug them in, and the recursion becomes just that. Kernel in the L+1 layer is given by CB plus CW times A2 times KL. And we can easily solve this given some time, but let me simplify my life for this lecture by setting CB equal to 0 and some further defining this object chi. So just to show you in equations, I'm just setting this CB to 0, and then I'm just defining this object to be chi to simplify the equations, sort of. And with that simplifying assumption and some notation, you get chi L+1. No, the kernel in an L+1 layer is given by kernel in an else layer, but then just by multiplied by chi. So as you go deeper in a layer, you're just continually multiplied in by this constant chi. Okay. So this is very simple equation. We all know how to solve this, and you get this exponential solution as you do. So k in the else layer is given by chi to the L-1 times the one that you had in the first layer. And in the last lecture, we determined the kernel value or the 2-point correlator. We evaluated them, and this is what we got: the CB plus CW times the norm of the input normalized, and we are setting CB to 0 here. So in summary, in the setup, what we have is that the KL is given by exponential solution with chi defined as such, and then K1 defined as such. Okay. Now, like you notice that so now let's see what happens since we've done the math. So chi is greater than 1. When chi is greater than 1, what happens is that this k keep growing exponentially as you go deeper in the network. So what's happening is that it's exponentially exploding, this signal, and going back to the definition of k as the norm or the leading term in the norm of the pre-activation. Basically, what's happening is that the magnitude of the pre-activation is expanding exponentially as you go deeper in the network. Okay, so that's pretty bad. Like especially like when you reach the network output in a deep network, like that would be let's say that it's order million because it's exponentially growing, and then your target function is like of order 1, and you're so far away from what you want to achieve at the end of the training. So that's pretty bad place to begin. And similarly, if in contrast, if chi is less than 1, and if you go deep in the network, what's going to happen is that it's getting multiplied by constant less than 1 again and again, so it's exponentially diminishing. So what happens is that in this case, all the signal is being eliminated. Everything just approaches 0 so quickly that once you get to the output of the network in a deep network, you have very much no signal from the input, just 0, 0, 0, 0, 0. So that's both bad. So like in general, like we learned that if you take a deep network with generic choice of hyperparameters, then this is you either suffer exploding or vanishing signal program. But if you do fine-tune the initialization hyperparameter so that the chi is equal to 1, then you are saved from this exponential program. So, and then we call critical signal propagation in analogy to the critical phenomena in physics, but it's just a way to say that the signal is preserved as you go deeper in the network. And in this case, KL is constant, so you're multiplying just by 1, so you get equal to the input kernel norm, and it's constant. Let me denote that with K star as to say that this is kind of fixed point equation, fixed point solution to the recursion. And to get more closer look, this is happening in particular when you set the chi equal to 1, meaning that you're setting initialization hyperparameter for weights to be 1 over A2. And by plugging the definition, it's 2 over A plus square plus A minus square. And one thing to note is that if you put Ledoux activation function for this, so A plus equal 1, but A minus equal to 0, then you're getting CW equal to 2. And that reproduces the well-known chi-mean initialization for Ledoux activation function. And this chi-mean initialization is known to be empirically good for training Ledoux architecture with Ledoux activation function. And it was discovered more empirically, but with a similar kind of reasoning, where like chi-mean considered that the distribution of the network activation pattern should be preserved from layer to layer, and he reached by experiment that this value is good for that. But here we have an analytical understanding of how to do that, and also we know how to generalize to any scale invariant activation function. And we will later cover how to generalize this further to any activation function that you might concoct in the future. Okay, so that was the practical lesson, and I'm gonna try to box with the orange mark for any practical lesson that we will try to emphasize. And finally, I'm gonna leave you as an exercise, maybe tonight, for the case where you set CV, the bias variance, to non-zero. And what you're gonna find is that you have some parallel growth of the kernel in that case. Well, generally exponential, but if you tune chi to 1 and then CV non-zero, then you have parallel growth of the kernel, which is suboptimal in this case. Okay, let's move on if there's since there seems to be no questions. Yeah, so we can now, in terms of the NTK mean recursion, so I just reprinted that recursion relations, and I'm gonna, so what you do is same as before. So we have to evaluate some integrals as before. And so this sigma thing is same as before, A2 times K. And yeah, so that's just representing the equation from before. And you have this new Gaussian expectation you have to evaluate, but then this is actually simpler than before, because A prime, sigma prime is same constant for positive axis and negative axis. It's just A plus on the positive side, A minus on a negative side. So you have square of that, and then half contribution from each positive axis and negative axis. So you have A2. Okay, so plugging them in, you have this simpler looking, or actually the simplified recursion or specialized recursion for these activation functions. And it's given by this thing. One important thing to note is that this last term is CW times A2 is same as chi that we defined before. So that's something to keep in mind. And then you can plug that, use that notation and write down the recursion as such. And we can now glean some less physical lessons from this. But before going there, I guess there's one question by Darcy.
Hi, yeah, so my question is about the earlier slide when we defined criticality for the first time. So, my understanding of criticality, which is from a couple of Google Brain papers that came about that explain this, is that how they define criticality is that they, instead of looking at the kernel directly, they normalize the off-diagonal entries of the kernel and call it a correlation C.
Right.
And their scheme only works for bounded activation functions.
So they worked out the little well, so it's the same. So okay, thank you for pointing that out. So it's the same sort of same notions. That they studied the how the kernel propagates through the network, and this, which is exactly what we're doing today right now. And there's a series of paper by Surya and Jasha, and they're really nice. So for little activation function, it's same. A few remarks on that. So one is that so one is that we're going to actually connect the same criteria to other physical things. Like they studied kernel, but they didn't study NTK because NTK didn't exist at that point. So we are now going to be able to connect this to lesson on exporting and banishing gradient program in the next slide. And another thing is that, well, they heuristically studied that, but then we can make it precise, very precise. And the other thing is that there are two criticality conditions for general activation function, as I'm going to discuss, and they didn't emphasize one of them. Like there's two conditions. One is kind of preserving the either NTK in retrospect or how the two input get close to each other. So they emphasize that, but then there's also the norm, how the norm of the input propagates from layer to layer, and they kind of last on to the former than the latter. And finally, well, I can comment more on this when we come to Tanch activation function, but let me not do that right now. Yeah.
So yeah, thank you for bringing that up because I had a question about that. I was just waiting for you to make that point. Anyway, another related question was that in this case, if you add a non-zero bias variance, then instead of vanishing completely, the signal will probably saturate at some non-zero value, right? It will exponentially converge to some non-zero number.
Right. So if you turn on CB, and if you don't tune CW, then either it converges exponentially to some given number, or it would explode away to infinity.
Yeah. So in the I refer to it as an ordered phase. So in that, if it converges to some non-zero number, then that's not completely vanishing, right? And
right. So, but then what's happening is that basically you are squashing every input into one sphere. Right. So you're killing like the norm information of the norm.
Yeah.
And what you can kind of show further is that that may be okay when all the labels are same norm, but then when you want to do functional approximation where the target output can have different norms, you're actually going to eliminate that information. So that would be problematic. And that's another thing we discussed in our reference.
Okay, thank you.
Yeah. Oh yeah, thank you for us bringing that up, and keep bringing that up if I touch on it later. Cool, thank you. Okay, cool. I was there, and then I was alluding to NTK, and I said something about integrals, and this is what we have, same chi. This is what you have, and now kind of answering your question. Well, we've already answered sort of, but then in detail. So now when chi is now greater than 1, not only you get this kind of contribution, but then you have each layer, you get this additive contribution to the NTK. But as you go deeper in the layer, like you keep multiplying that contribution by chi. So if chi is greater than 1, then this NTK would blow up exponentially. And why do I say it's exploding gradient? And that's because NTK is defined as the gradient of the pre-activation with respect to model parameters squared, essentially. So if this quantity is exploding as you go toward the network output, then this gradient is basically exploding. So it's connected to the exploding gradient program in the mean. Okay, so that's how you make it precise about the exploding gradient, how to make precise the exploding gradient program. And you can also talk about the vanishing gradient program. So like when chi is less than 1, what's going to happen is that you have this kind of vanishing gradient problem. But to be more precise, actually the NTK itself stays kind of order 1. But what's happening is that the contribution to the NTK from the model parameter in the lower layer is getting multiplied by this like chi less than 1. So basically, if you try to differentiate the network output with respect to the model parameter in the lower layer, that quantity becomes really small, exponentially small when you have chi less than 1. And in particular, when you try to train the network, then you cannot train the lower layer biases and weights. So you're kind of under training, or you're not maximally utilizing the resources you have in the network. So that's vanishing gradient problem for lower layers. And again, when you set chi equal to 1, then you're preserving this information of gradient through the network, again, where the critical parameter, initialization hyperparameter is given by this. And in this case, as again, from the previous layer, kernel is constant. But now if you plug that into this recursion and solve with chi equal 1, then you're getting this additive contribution from this first 2 terms. And basically the NTK grows linearly with the layer. And this satisfies initialization for the first layer NTK value that we derived in the last lecture. Okay, cool. So one lesson, so the one lesson is that, again, if you look at the gradient, exploding vanishing gradient problem, you reach the same conclusion that the critical initialization hyperparameter should be fine-tuned as such. Another lesson is that if you look back at how the network output updates itself under the gradient descent, it was given at the leading order by this global learning rate eta times NTK in the last layer times the derivative of the loss with respect to the network output, which is sometimes called residual or error factor. And so this product of global eta and NTK should be order 1, or smaller than some value, so that as Dan discussed, for the linear model, for the training to converge, error must be small enough to ensure that convergence, and that's given by eigenvalue of this matrix. And so basically it must be the order 1 or less. And if it's too small as well, that would be bad because it doesn't train much. So you need this whole thing to be order 1. And to ensure that, you have to have this eta times lambda BOW must be scale like 1 over L, where L is the depth, capital L is the depth of the network. Okay, that's another lesson. And finally, while at it, we can solve the recursion for 4-point connected correlator, so capturing the near Gaussianity. So I'm not going to go through that in detail right now, or I'm going to show you the details, but I'm not going to go through that in real time. And then I don't expect you to. So just try to focus on how it goes and just look at the results. So again, as before, we do a bunch of integrals, which you can do because it's so easy. And you get this recursion where A2 and A4 is defined as such, and chi appears again. And then you notice that if chi is greater than 1, this guy itself is exponentially growing, and if less than 1, it's exponentially vanishing. So you look at the criticality bias 0, where it's initialization hyperparameter set as 1 over A2, and you can get the close, you get this recursion, and this is constant basically. So you can add them up and you get the solution. And one lesson from this is that this 1 over n finite width effect is growing like 1 over n added from layer to layer. So if the hidden layer is more or less uniform, then you're getting 1 over width added L times. So like you have L over n, so depth over width ratio. And this is one of the recurring themes that we are trying to allude to throughout the lectures. But now like we have where it comes from. So finite width effect is depth over width, because at criticality, if you solve the recursions, then you see that the finite width effect accumulate linearly with the depth divided by width. Cool. So another before leaving the regime of this real of scale invariant activation function, let me allude to another concept, which is universality class. So one thing you notice is that aside from some differences in order 1 numbers, like A2 and A4 defined in terms of A plus and A minus, they're basically behaving in the same way when as far as like the depth dependence of the network is concerned. And that's why we could analyze them all at once. And you don't have to analyze the linear and ReLU and leaky ReLU each time, but you can just have it solved once and for all. And that's reminiscent of the concept of universality class in physics, but or statistical physics. But here, just a way to say that the myriad of the activation functions can be dumped into like one category. And one caveat is that the linear activation function is actually pretty special in this class. So when you do the finite analysis, like how the finite angle close between 2 inputs, you start to see the difference. And also when you go to higher order in NTK and DD-NTK, you get singularity when you have kinks, and then you don't for linear. But that's one caveat, just to be precise and complete, as boys like it. Okay, so if no more questions, I'll just generalize these lessons to other activation functions. Okay, so the principle of criticality, just to summarize, so in general, is the necessity of hyperparameter fine-tunings in order to avoid exponentially exploding and vanishing signal and gradient problems for deep neural networks. And we've seen that for scale invariant class, and we're going to try to generalize that other activation function. And in particular, for the scale invariant activation function, we've solved the recursion and determined that the criticality was attained by fine-tuning initialization hyperparameter as such, given in this equation. And that's one practical lesson. More generally, like let's try to solve this more generally. And the recursion, this in general has a fixed point satisfying this fixed point equation. So it just says that K doesn't change from layer to layer. So K star is equal to CV plus CW times discussion expectation evaluated with K star variance. Okay. So in general, like given some hyperparameters, initialization hyperparameters, you have a discrete number of fixed points in general. And expanding around this, so for now, like I'll describe, well, we can describe how to obtain these fixed point values, but then let's for now assume that such a thing exists and we can find them. Let's expand around this fixed point, K star. So what you have is that so now KL expressed as K star plus some deviation from that fixed point value, and that's what we have. And so this is just linearization of the recursion equations. This is typically what you do to solve the nonlinear equations or get handle on the nonlinear equation. So you have delta K in an L plus 1 layer given in terms of something times KL plus something higher order, which we can truncate for now. And here this chi perp parallel is given by differentiation of this guy with respect to K, or the whole thing, but CV is constant. So that's evaluated at K star because you're linearizing around that point. Okay, so to summarize, in the previous slide, we have K star dictated by some initialization hyperparameters, satisfying this equation, fixed point equation. And around that, if you linearize, then you have this recursion equation for linear deviation around the fixed point, and chi parallel is given by this equation. And actually, this is Gaussian integral, so you can differentiate K inside the integral, and you get more friendly sort of looking Gaussian expectation, but it doesn't matter which one you use to evaluate them. And the physics of this is that if the chi parallel at K star happen to be greater than 1, then you start the signal at the K star, then just exponentially expand away from that value. And in general, it's going to go either to infinity, or if there's another fixed point, it's going to go there. So you can analyze that fixed point as well. And another possibility is that the chi parallel k star is less than 1. In that case, again, like the signal just collapse onto the sphere, or if k star happen to be 0, it's going to collapse exponentially to 0, and you're going to have some corruption of some signal information. And again, by setting this guy to 1, you have critical propagation of the signal. So this is one of the conditions you want to satisfy, and let me just box that equation. And just to remind you, this k star is a function of CB and CW. So you have 2 variables and 1 condition, and if you have another condition, you can completely specify CB and CW that you want. And to find that, let me look at NTK mean recursion, and this is just reprinting. But if you look at this term, which is multiplying the NTK contribution from the previous layer, which was the one that was responsible for exporting and vanishing gradient program in the scale invariant case. This is just a generalization of that. And you can define this chi perp to be this guy. And if this object at fixed point is greater than 1, then you have exploding gradient program. If less than 1, vanishing gradient for lower layers. And if it's 1, it's the right balance, and you have critical propagation of gradient information through the deep network. Okay, so you have this another condition, chi perp is equal to 1. So basically, you have 2 criticality conditions for the 2 hyperparameters. So what you do in principle is that you set some initialization hyperparameter, you find k star, and see whether these conditions, chi parallel and chi perp, is satisfied or not. And given 2 variables, 2 hyperparameters, and then 2 conditions, this uniquely determines what the CB and CW must be to satisfy the criticality conditions that the signal propagates critically and gradient propagates critically. And just to kind of, as a sanity check, the scale invariant case, it was a little bit degenerate. So both of the chi are given by CW. If you evaluate, it's given by CW times A2, which is chi that we defined before. So in that case, actually, their notion agree. And that's why we had this common factor chi there. But in general, you have 2 hyperparameters, 2 conditions. I think there's a question from.
So is there an intuitive reason why we're calling one of them parallel and the other one perpendicular?
Oh, this perpendicular ones is for the very generic, like you have to ensure them for gradient to propagate, which you want to ensure all the time. And parallel one as well. So in a scale invariant case, it's degenerate, and then in general it could be different, but it's more important when the inputs norm are different, or the output norm and input norms are all different. Can I say more about that? I guess that's one case where I know for sure to be important, but in general, you have to, there's a bunch of conditions that makes you want to ensure both of them. And also this, and chi perp, this one comes into the generalization error that I'll discuss soon.
I was asking also that like an intuitive reason for the name, like that one of them is called parallel in particular.
Yeah, so
right.
So it was 1 and 2 in the Brain's paper, and here like the reason was that you're considering that in the original, in chapter 5 or reference, like what we have done is that there's parallel perturbation of the input, which corresponds to the change in the norm of the input. And then there's a perpendicular one, which is also going to not changing the norm. And they give rise to 2 different conditions. If you look at the 2 input 2x2 kernel, But you can realize that the NTK is sort of doing differentiation with respect to the perpendicular directions in high dimension, and that's why you get, just by looking at single input NTK, you get this chi-perp. That was the pedagogical simplification I made for this, but the name comes from more Zoro analysis of two input kernel.
So it doesn't exactly have to do with like the diagonal and the off diagonal entries of the 2 by 2 kernel, does it? Okay.
Sort of. So like basically, the parallel one is the addition of all the 2 by 2 components, and then the perpendicular one is like diagonal minus off diagonal, basically.
I see.
Like how like these are individually changing from each other.
Okay, thank you.
Maybe James.
Thanks, Joe. I can also ask this at the end if you don't have enough time, but it was like a quick question. If I wanted to use, let's say I had a network that I was writing in TensorFlow or PyTorch, and so this is like kind of for initialization to go well, and you were saying that the variance of the biases should be 0. So does that mean I just like, and I also thought that the mean was 0. So does that just like set everything to 0 and don't have biases?
So for scale invariant class, you don't want to have biases at initialization, but because there's some weights that breaks the permutation symmetry, you start to grow the biases as you train them. But at initialization, you want to suppress them completely.
Okay, so even if they are at 0, like they'll actually get trained.
Yeah, they do. Yeah, that's a good point. Yes. Cool. Okay. So given this, also, okay, I said that this is the general conditions. Now let's see how that applies. And for example, just if you study the tanh or sign activation function that people sometimes use, you get this criticality condition. I'm not going to detail the derivations, but this is what you get, just to show you that you can get something. And here you get a fixed point in particular at k star equal to 0 with this criticality condition satisfied. One caveat, and that's why we say, and this sort of, there's category of activation function, you kind of falls onto the same behavior. That's why I say k star equals 0, universality class. And one thing you might worry if you're very attentive is that k star equals 0 isn't that bad, and it's not going to be, because we're going to see that it's not going to be exponentially vanishing the signal, but then it's actually parallel, which is really mild. So even if you have pretty deep network, it's not going to kill the informations. I'll come to that later, but just not to worry you. For more general smooth activation function or analytic activation function, I can Taylor expand the sigma as such, and you can show, if you like, some proofs that this condition, criticality condition, is met with this k star equals 0 if and only if the first component sigma naught is 0. So it's crossing 0 at origin, and then sigma 1 is non-zero, meaning that it's crossing with non-zero slope at origin, such as tangent sign, but not for sigmoid and perceptron, and I'm going to show you why they fail. Okay, so criticality in general in this case is attained by CBCW is equal to 0 and 1 over sigma 1 square, and for sine and tangent sigma 1 was 1, so that's why I had 0, 1. So that's a practical lessons for smooth activation function that crosses 0 at origin. And as I alluded to 2 slides ago, there's a parallel decay of kernel, not exponential decay at criticality. So it's very mild. So even you have pretty deep network, like say 100 layer, which is pretty deep, you have not e to the something 100, but then just 1 over 100, which is still numerically tractable. Like numerical accuracy wise, it's not like hitting the floating point precision or anything. And also again studied how the 4-point connected correlator or finite risk effect behaves, and it's going to go like 1 over n, 1 over L in particular. And I'm not going to describe this, but there's another principle that this is one slide where the learning rate parameter like lambda and lambda w is better to be layer dependent. And for tanh and sine activation function, you can show that the to avoid some polynomial version of exploding vanishing gradient problem, i.e. to ensure that there's equal contribution from all the layers to NTK, then you want to rescale, especially the bias learning rate, to be 1/L. So you amplify the effect of learning for lower layers compared to the deeper ones. And you can do this for any smooth activation function that crosses 0, but then it's simpler formula for all smooth functions like tangent sine. And two slides for other kinds of activation function. Oh, there's one question from Siddharth.
Hi. So for the scale invariant case, we had that the power law for VL is order of L over N, right? And in the previous slide, the power law is 1/NL. Are there what implications would there be on the nature of activation function from here?
So I'll come to that in the next section. Great. So yeah, let me cut through that. So, and Tian Yu?
A quick question. So will those finite order perturbations change your critical points?
Yes, they do in general. So like you can actually have to shift the initialization hyperparameter by 1/N effect, and you can compute them.
I see. So is there a case where those perturbations are irrelevant?
So in a scale invariant case, it's irrelevant. But for tangent sine, like it starts to be relevant.
Thank you.
Cool. Okay, so for some other activation function, you can compute this for like swish. Let's look at some variants of ReLU, smooth version of ReLU, and for swish and GERU, you can compute them. And this is what you get. This is what you should be using. Yeah, but not all the activation function actually accept this notion of criticality, and especially like not all the deformation of ReLU. So for like soft plus was meant to be a activation, well, the smoothing of ReLU activation function, but it turns out that the criticality condition cannot be met for this activation function, and also sigmoid that people used to use back in the day, and perceptron that people used to use really back in the day, cannot satisfy this condition. And this now explains why they didn't work for deep neural network. And so never again, like let's not use them again ever for deep learning. And we now know the reason why we shouldn't. Okay, so to summarize this section, so there was this necessity to hyperparameter fine tuning in order to avoid this notorious problem of exponentially exploding vanishing signal gradient problem for deep network. And now we have a principal way to identify critical initialization hyperparameters, and also to give some no-go for some activation function that if you come up with them, you should go back and cook up some other activation functions. Okay, finally, well, yeah, finite with effect and deep learning. So let me, in the interest of time, oh, by the way, one thing I should mention is that after this lecture, Dan and I will have question and answer session. So we'll just stick around and answer any questions. So let me go through this quickly, but then this concerns Siddharth's question, so let me go through that somehow. So for the scale invariant class, we had this basically at criticality kernel was constant, and one of finite with effect was L/N. Whereas for the K star university class, K star equals 0 university class, you have 1/LDK for both of them. So you might say like maybe for each university class there are some difference, but actually like what goes into the answer when you try to study, for example, the prediction of the network, it's not in each individual V and K, but it's some combined ratio of them. And I'll just spare the details. You can do some dimensional analysis, and I can go through them in a later session. But you can do some dimensional analysis, and you get this ratio is the proper one. And for both of them, this scales like depth over width. And this sort of answers, hopefully, Siddharth's question. And finally, you can do the same for all the finite with effect that we have. And basically, I display the recursion relation for all the tensors or the numbers we had in finite with 1/N effect. You can solve them. You can get the dimensional dimension ratio for them, the answer is that all of them just goes like depth over width. And in particular, the fact that the DNTK effect and DNTK effect, which are responsible for the representation learning, says that the depth is good for learning the representation. As you deepen the network, you amplify the effect, the power of the deep network to learn the representation of the world. But it's not all good, because there's actually the fluctuation effect that is getting also amplified. And like what this means that even if you tune the hyperparameter so that the gradient the gradient is preserved across the network or the layers, actually each individual instance of NTK start to fluctuate a lot. So sometimes you get more exploding gradient, sometimes you get more vanishing gradient. So you have to tame this fluctuation as well. And this intuitively leads to the notion of sweet spot, which will be covered as a part of lecture 5. And also you can go ahead and read appendices A and B. But basically, as a function of depth over width, there's some regime. So if it's 0, then it's infinite width limit. It's not deep. You're not employing the actual effect of the deep power of the deep learning, representation learning. And as you crank them up, there are regions where like you start to learn the representation or useful representation from data. But if you crank them up too much, then the network becomes chaotic and fluctuate a lot from instantiation to instantiation, and that's overly deep. And we'll try to have some way to estimate this number. Okay, finally, let me use 5 minutes to say why criticality is important. So as we covered today, and you can read more in a reference, the taming, it was good for taming exploding vanishing kernel problem or the signal propagation problem. And it was also good for taming exploding vanishing gradient problem, which we covered today. And there's also, if you try to compute the Bayesian evidence, then which whose computation you can find, you find that it's going to take a while to explain the Bayesian inference or lecture 2 to say that, but then like there's model selection, and this model selection criteria picks up the critical hyperparameters as well. So many evidences. And then the last thing is that it's also a good, it ensures a good generalization error for some nearby inputs. And let me say a little bit more, because people talk about generalization in this lectures, in the summer school. So just to put into the context, let me describe the generalized notion of bias variance trade-off. So in general, you have this bunch of training inputs in the input space, and I should never draw things in the 2D, but I do. Okay, so and then you have some test input. For the schematic, it's fine. Test input, and you try to predict how what the output for this test input is, and the goodness or the performance of that test generalization is evaluated by, say, how different the prediction of the network trained network is from the true ground truth label of the test input. And square, you can insert basically 0, like, and take square of that. And you note that this first 2 term has mean 0 and then some variance, and that's what you have here. And this guy is just a number, so you can take outside the expectation and you get this square. And this first term has the interpretation of variance, like how much variation you have in the prediction as you instantiate and train the network from some seed to seed. And then the second term is a bias, like how much bias you have in your prediction on average. And here I say generalized bias variance trade-off, because it's a little bit different from the usual standard notion of bias variance trade-off, where you ensemble average over the realization of the training inputs. Here I'm looking at the expectation over the instantiation of the network, okay, for the fixed training input. It's the same notion, but same math, but then used conceptually differently. And the punchline of this analysis, so there are some analytical tractable case, especially if the test input is nearby one of the training input, you can solve this problem. And what you find that the deep network, when chi-perp is less than 1, becomes too inflexible and confident and too biased, hence, because basically every signal is collapsed. And on the other hand, if you have deep network is chi-perp greater than 1, the prediction would be too floppy and change from time to time. And also like it's very sensitive to the change in the input. So it's too varied and both are bad. And the sweet spot again picks up chi-perp equal to 1. And that's how you get one of the criticality conditions from the consideration of generalization error. So that was the end of the lecture. And this is a summary of 2 lectures. So in lecture 3, I covered the principle of sparsity for wide neural network. And at infinite width, you had this very simple distribution, but too simple. I back off that limit. And then you get the 1 over n correction, which we now realize to be L over n correction. And you have to keep track of a few more things. And then like today, I covered the principle of criticality for deep neural network. And to ensure the critical signal and gradient propagation, you had to tune to the criticality for initialization hyperparameter criticality, and we know how to do them. And we've also seen the emergence of university classes as we went along. So I'll take questions, and maybe Gadi.
Hi, sure, thanks a lot. I have kind of a more broader question about kind of the whole perturbative approach. So I wonder, I mean, could you have like any guarantees on when only the leading correction is kind of sufficient? I mean, I guess that if the width is small enough, then you might want to have like more terms in the expansion.
Right. So we know that when at the leading order, like when the depth of width is small enough, the leading contribution we described is all you need for the deep the train network distribution, and both at initialization and after training. But when you have, say, like depth of width is 0.1, so that the like 10% you are missing like 10% of the accuracy. So to be quantitatively more correct, you might want to go to the higher order, and you have a bunch of more terms, and the model becomes a little bit more complex, that as we kind of cover hopefully in lecture 5. But we in general believe that its expansion is always over the depth of width ratio to some power. It's probably asymptotic series.
But it could be, I mean, if you just like think like simple-mindedly, if you have, you have the series expansion for 1 over 1 minus x, and say, say x is pretty close to 1, it's 0.9, then you need, I don't know, like 20 terms to get like right to get a good position.
Okay.
So
good. So like we have So there this part of the approach breaks down, but it turns out that they can, as I kind of alluded to, the regime where the depth is too large is also useless in practice, because the NTK
but you don't have right. So you don't have. I mean, when you say so it's you're always, when you're saying large or small, it's always the ratio of depth to it. I mean, it could be that both are kind of. Could be that it's only like 2 layers. I don't know. It's only like 2 or 3 layers, and the width is only like 10. So the ratio is small.
Right. Yeah. So
it
there's
doesn't
also
have to be like.
Yeah. So there's like L over n square effects and so on, and then we are just picking up the most leading order one, because we are kind of amplifying the effect by depth, right? So we are going to study deep network, and that's
Right. So, but my my main question is, so do you have like any like universal or general criterion for when this kind of breaks down, or is it kind of, take your network and then try it and see how good it fits, and hopefully, like you should I don't know, I guess that you should have like good intuition that hopefully it would be kind of a good approximation, or something more precise to say.
Right. So Dan will cover, I think, the prediction, how the prediction of the network changes when you add these finite risk corrections, and you can try to see how accurate those predictions are. But like there's one criteria also, which I didn't want to mention today, but then I'll mention it anyway. So in Appendix A, we compute mutual information, and actually like mutual information between the neurons in the same layer for a given input initialization. So it's like an unsupervised criteria. And it turns out that as you increase the depth, it actually maximizes at some ratio and then decrease again. So there's actually some notion of optimality in terms of mutual information, or how much wiring you can do in a network. And there's actually characteristic scale for the depth over width ratio, and it depends on activation function, on whether you have residual connection or not. But these things you can compute. If that helps.
Did you say the mutual information at initialization?
Yeah, so you have initialization distribution of the neurons, and you ask what the mutual information is for on a different neurons in the same layer, and you can compute them.
Are they not IID?
No, so because like you are now because of this non-Gaussianity, you are correlating the different neurons. So at the Gaussianity in an infinite limit, there are IID, so there's no mutual information.
You mean, I see. You mean like the pre-activations or the activations?
Yeah,
okay,
exactly.
Sure.
Okay, in a deeper layer. So that's one precise criteria that you can.
Okay, and so could I ask like one more? Sorry because I'm very interested in this. So can I ask one more question?
Yeah.
So like in terms of like you said that you need the finite width effects to in order to explain feature learning.
Mm-hmm.
So could you say something about, I mean, how well, or like something quantitative about how well it captures the feature learning? Because I can imagine like some scenarios where a finite network will have good feature learning properties, but only the leading finite width correction will capture only a small portion of that.
Yeah. Okay, so what we have computed is that you can compute the changing NTK, for example, and that's linear order one depth over width, and so that's indicative of why I said what I said about the feature learning. So one thing that's kind of coming back to what you raised before is that you can try to do the generalization error computation to the second order, which we didn't do. Like mutual information we did to the higher order, and then we find this optimality. You could, in principle, carry that to higher order and then try to see that the generalization error, which is like the more very physical criteria, so to say, will probably pick up this optimality. But this is taking one leap of faith, combining two ingredients that are like the notion of the criticality was first picked up by looking at the initialization distribution, the kernel. But that actually generalized if you look at the critical gradient condition and the generalization error. And then hopefully this mutual information, which is about the prior, could generalize to the generalization error notion. But that's a gross computation that we haven't done yet.
Thanks.
First, and I'll take Frederick's question.
Yeah, hi. Thanks for the talk. So in my interpretation, I think your work is really cool in the sense of probing into different problems or different aspects of learning.
Mm-hmm.
And I wonder whether sometimes it would be good to, once you have identified a problem, to zoom out again and then think of practical solution instead of directly jumping, from your calculations to practical conclusions.
Mm-hmm.
And one example here would be, your initialization, your suggestions for picking initialization and learning rates is A, kind of very cumbersome, and B, you kind of have to do initialization plus layer-specific learning rates or something like this, right? And you have to do the preconditioner.
I mean, these choices you have to make anyway in practice, like before launching the job. But then now we don't have to grid search what the optimal conditions are. We know.
So that's a great point. But in practice, once people do, let's say, batch normalization or ResNet, or they use Atom instead of SGD or anything like this, then your calculations don't hold anymore, right? So you have to do them from scratch, in a sense.
In principle, yes. Like, but for different architecture, you have to do new computations like convolution. Like let me back off and say that the like general philosophy that you can study the recursion and then try to study the signal and gradient propagation stay true for deep network. Like that's what you should be keeping track of. And for NLP, we did this analytically, and you can also do with visual connections as well, as we've done. Like convolution, you have to do this again. For self-attention block, you have to do this again. So, sort of like what we are actually trying to do right now.
In a sense, you have to do it again if you use Atom instead of SGD, right? Because then
Atom. So SGD we know how to track, but the Atom we don't know.
So my point is, in the sense that, you know, for the forward pass, this exploding thing has been studied for a while, and I think in practice people converge to an algorithmic solution, which is something like batch or layer-wise normalization, right? So this is used a lot in practice. Question would be, you know, once you identify, sorry.
Oh, sorry. So one thing is that I think with these things were kind of added ad hocly without knowing this kind of systematic approach. And then if we implement this, then like we can probably reduce at least the need for these things. Of course, they are like more model parameters, so they are going to do a little bit better, but I think we can stabilize the network more with this approach.
So I agree partially. It's just the matter of, you know, once you're in practice and you use something slightly different, then all of a sudden you'd have to do this entire thing again. So I wonder whether you can have a practical solution. Let's say, you know, you identify a problem with your approach, which is great, and you give some direction in terms of where to go. So like, let's say renormalizing or choosing specific learning rates or preconditioners. But in a sense, wouldn't it make sense to then take it one step further and make this again an algorithmic solution so that it's much more flexible in real life?
I was meaning that they have some empirical procedure to do this.
Yeah, like batch normalization.
That's what you meant.
Just now for the backward pass.
Right. So I think so. For the forward pass, even if you include them, I think the conclusions stay the same, right? Because like they're usually initialized to 0. So at least like even with the inclusion of these things, you should. Well, okay. Let me not say unfound thing. So yes, you have to do, and then I think that's important.
Yeah. But I mean, we can take this offline. Right. It's a longer discussion.
But it's like a framework for, if you know physics, like standard model, right? Like there's quantum field theory, which is a theoretical framework, and now you apply to quantum electrodynamics, and then you have to fine tune the model. You have to calculate them, and for the standard model with QCD, you have to do another calculation. But this formalism gives you a framework to think about it, and that's good.
Yeah, I fully agree. I mean, that's great. That's great. Just the setting that's slightly different from physics, because in physics you have some kind of ground truth, presumably, and here you have common practice. That's common practice at the moment. So while you're computing something, you're also changing the common practice. So there's this feedback loop, right? So on a high level, it's a slightly different situation.
But in principle, you can accelerate this feedback loop, right? Because you eliminate some part of the trial and error. So that's what we are trying to accomplish here.
No. So I totally agree. I mean, from that point of view, I really like this approach.
Great.
It's great.
Great. Yeah. Okay. But yeah, my hope is that the theorists and practitioners talk to each other.
Yeah. Cool.
Which what I'm doing. Yeah. Okay, Varun.
Yeah, I was wondering if you can go back to the slide where you were looking at the propagation of the NTK. I'm just
Okay.
wanting to make sure if I understand something correctly, or maybe
Okay.
I don't. Over here, so
maybe
how,
for the scaling invariant case would be simpler.
yeah,
maybe.
how did you define the H thing? Like you wrote it down here somewhere.
Yeah.
Yes. So this is a okay, yeah, I see what you have here. The question I had was like at least like some part of the approach that I'm not really comfortable with, but like just because it doesn't go with my intuition, is that we usually do things in back propagation when we're doing things in practice, right? And so like the way that you're talking about things either like having an exploding gradient or vanishing gradient, that is like if I remember correctly, like the gradients for the later layers, because we're doing back propagation, those will seem not too big, or I mean, I haven't looked at this in practice, so it might be wrong. They don't get too big for the exploding portion, and they don't get too small for the vanishing problem. But when you bring all the way to the beginning, then it's like you see that. But in this case, you're saying it goes like the opposite way. So I guess like I'm curious.
Right. So mathematically, our approach is going forward, right? Like as I emphasized, and then answering your question last time.
Yeah.
And here again, like you can track the contribution to the output gradient respect to lower layer, and then try to study how that changes as you deepen the network. And that has a this chi multiplied again and again and vanishing. But what's happening is you can, of course, after the fact, think about backward way, right? It doesn't matter. Like you're computing this object, which is a multiplier of the whole thing. Sure. And you're noticing that this chi is multiplying the whole thing as a chain rule. And yeah, so that's how.
I guess like I was wondering if like because the chi that you compute here is for the forward methodology, and if you were to go backwards, would you end up having the same chi?
Right. So for the scaling invariant, it happened to be the same, but then as kind of noted, for the general activation function, it leads to the defined notions. Because let me see. So you had these two criteria, and this chi parallel was the forward pass.
Oh, okay, yeah, okay, I see.
And and then chi parallel perpendicular is the backward, if you will.
Okay,
So,
this makes
yeah.
It might be helpful to say that to do that analysis for the exploding and vanishing gradient, you do need to consider the backward pass. You just didn't, which you've done. You just didn't put it in the slides for simplification of a talk. But and the component that goes into it is about the NTK, but there's more involved analysis you can do of the backward pass.
Gotcha. Okay. That sounds good. Thanks.
Maybe I'll make a comment too, if you don't mind, Cho. Just very
yeah, of course. Yeah.
Just in response to your question, Varun. Like if you take some weight in some layer and you try to differentiate, the output of the network with respect to the weight, like algorithmically, you're going to calculate it by some kind of backprop thing, but in that backprop, it factors through the derivative of the output of the network with respect to the neuron into which the weight goes.
Yeah, I was wondering, because like in essence, when you're doing backprop, the information of the first layer or like in the beginning of the network is like encoded in that. So it's like you're also getting that. I just didn't see it like easily.
Yeah, right. Right.
The full analysis is in I think it's section 9.4 of the main reference, but it does the backwards thing, and there's like 3 factors that you consider, and the important one is the one that Cho discussed.
Gotcha. Thanks.
And also it discusses how this chi parallel comes into that equation. And I guess Darcy.
Yeah. So it's probably like a kind of follow up of what I asked earlier. So you mentioned that the Google Brain papers only did one of the two. You had 2 conditions. They only had one because they only considered the forward pass, I assume.
Emphasize is maybe proper word.
Yeah. Okay. They only emphasize the forward pass, and using that, if you look at
they emphasize this chi perp one, but yeah.
Right. So when you yeah, if you look at the two-dimensional plot of initialization sigma W and sigma B, in that phase diagram, they only had a critical line.
Right. So that's why that was picked up by this one condition.
So is it true that you get that critical line, basically a condition on what sigma W should be from the forward pass, and then you get the condition on sigma B from the backward pass? Is that in general true, or it's like it's more a coupled thing?
There are, so if you do only consider forward pass, then you get both of them only if you look at the two input case. If you look at a single pass, then the forward pass gives you parallel, and then the backward pass or the gradient gives you perp. But one thing I should mention is that if you look at the 2D plot, as you mentioned, and then see where the test performance peak, it's close, getting better at the origin, and meaning that it's getting closer to the one that's picked up by this other conditions empirically. And I think that's why, because like this was scaling variant, well, their chi-parallel not setting equal to criticality will have the norm exploding, so that's bad eventually.
Maybe I can also just add, like the kernel is a 2x2 matrix, so there's two fundamental components. One is, and the reason show only gets one in when talking about the kernel here is that he's simplified by only talking about one input, but in general, for full generality, you have to talk about two inputs. And so then you get the two conditions about depending on how the inputs relate to each other, and both are important. And by fixing those, you automatically fix the gradient problem. So everything is actually very much coupled, but it's much simpler if you or it simplifies when you only consider one input, as Sho was describing.
Yeah, thank you. That's much clearer explanation. I think that unless Sidak has question, that's I guess all we have. Or Gary.
Sorry, I just forgot to lower my hand.
Oh, okay.
But I can ask one question since you have asked. So it's a very quick question. So I really like this direction of work, and I would want in the future no ad hoc methods like batch norm ever in neural networks. And so I'm wondering if it is possible from your framework, from your analysis, to understand what batch norm is actually doing.
Let me answer that without answers. Well, I don't want to say any imprecise things.
But rough, let's say, intuitions.
So our hope at one point, well, it still is to eliminate this ad hoc method. Now that we have more systematic way of thinking about how the propagation should be preserved. And we are working with practitioners right now to implement them in a more state-of-the-art architecture. And there we can gradually experiment that how, after fixing the problem with our formalism as much as possible, can you start to reduce these norms, batch norm, layer norm. Some of them may stay to push your state-of-the-art accuracy a little bit, but we'll see how that goes. But I'm kind of being hesitant to say, because this would be on YouTube and it's going to stay forever, semi-forever. So.
Okay, that's smart. Thanks.
Yeah. And I guess like maybe we can we can stop the formal talk here, and then we can just get into more informal question and answer sessions for those who are interested. Boris?
Great. Yeah, that sounds perfect. Okay, well, thanks very much for a really nice lecture show. I really enjoyed it, even though I knew most of the content. It's still nice to see it presented in a kind of crisp way. Yeah, thank you all very much also, and see you everybody tomorrow.